Hi, is there a Michael in the room? Michael, can you stand up? Thanks. This completes the mic check. Now successfully given up twice.
Okay, good morning, everybody. I want to welcome you to the containers track this morning, and I'm happy to introduce Robert Richardson, who's going to be giving us a talk on building stateful workloads with Kubernetes. Thank you.
Sure. Thanks. Thanks for coming, everybody. I'm really excited. Here's the part where I tell you I'm definitely going to post my slides on my site tonight. You're going to check tonight, you'll check tomorrow, next week, next month. In about 3 months, you're going to get tired of pushing refresh, and you're going to email me. And really promptly in 6 months, I'm going to reply, yes, I'm definitely going to post them on my site tonight. And I'll never post them at all. Which is why if you go to robrich.org right now, you can click on presentations up here at the top. And here is building stateful workloads in Kubernetes. Here's the slides that we're going to look at right now. They are online right now. Achievement unlocked. While you're here on robrich.org, click on About Me, and you'll get to this slide that talks about some of the things that I've done recently. I'm a Microsoft MVP. I'm a friend of Redgate. AZ GiveCamp is really cool. AZ GiveCamp brings volunteer developers together with charities who otherwise couldn't afford software services. We start building software for them Friday after work. Sunday afternoon, we deliver that completed software back to them. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for AZ GiveCamp. Or if you'd like to see a GiveCamp in your area, then reach out to me and let's see what we can do to get a GiveCamp in your city as well. I do similar things. I do Git and Docking with gitgrit.com. And so if you like what you see today and you'd like to see this in your organization, reach out to me and we can definitely make that happen. One of my claims to fame, the thing that I'm most proud of, is that I replied to a .NET Rocks podcast episode. They read my comment on the air, and they sent me a mug. Woohoo! So that is my claim to fame. That's really cool. So we're here to talk about building stateful workloads in Kubernetes. We talked about this guy. So stateless and stateful. So here's a stateless workload, and if you were with us yesterday, we did similar things where a user comes in, they'll hit the ingress controller, the ingress will point them to a service, that's the load balancer that goes across all of the pods, and then a pod is that wrapper around the container, and we got this. This is what Kubernetes does, and it does it really elegantly. Score. But this isn't really what our application looks like. Our application looks like this, where we have the ingress controller, but the ingress controller needs a little bit of state. It needs the certificates that it's working from. The containers need to reach out to a data store, or maybe they need to reach out to an object store. And so they need to be able to save stuff that is durable beyond a pod restart. And then they need the configuration data of how do I get from here to there? Which database do I connect to? How do I know how to authenticate to that data store? Those are the pieces that aren't built into this model. And that's what we're going to look at today is how do I get state into my Kubernetes setup? So state. What is state? State. OK, that was a lot more funny for me than for you. State. So state, it's persisting things beyond the current lifetime. Now that lifetime could be a request or a response. The lifetime could be a machine restart. The lifetime could be a function call. Our goal is to persist data beyond that immediate lifetime. So what types of state do we have? Well, we have configuration data. We have secrets, the connection string to our database. We had databases. We might have file stores, or like an S3 bucket where we're trying to upload files to. And then we might have stateful services, where we have a cluster of machines that need to communicate with each other to keep their service up and running. And let's dig into each of these. As we dig into each of them, we'll look at kind of the pros and cons of each approach, how we connect to that in Kubernetes, and how some Kubernetes abstractions help us in this realm. So singleton services. That one kind of needs a little bit more explanation. What I mean when I talk about singleton services is a thing that keeps going and that needs to be able to communicate among itself. So I may have 3 nodes in my Kafka cluster, and I need to have all 3 nodes, or a subset of those, to be able to build quorum across my Kafka cluster. Or I may have a database where I need 8 or 12 nodes to be able to partition my data correctly and keep it highly available. These are those singleton services where I need to have machines that work in very specific ways, and the machines need to be able to communicate with each other in very predictable ways. Any questions so far on state? And just saying, those states are really cool too. If you can get those states in your Kubernetes system, then now we're talking highly available. OK, so one of the things that's really cool but annoying that we looked at yesterday is kubectl get all. kubectl get all will include all things that are stateless. It won't include all of the things. It'll only include all things that aren't stateless. Their theory is that if you can see everything, you might be able to discover secrets that you shouldn't have access to, or you might be able to delete and recreate things, and then they won't come back identically because they're stateful. So yeah, kubectl get all doesn't show stateful resources. And yeah, there's a whole bunch of GitHub issues about, I don't see my stateful resource. Yeah, you're right. And so for the most part, all of them are closed, will not fix. But if you really want to get all resources, there's this really cool thing, kubectl API-resources, which will list all of the resources. So if we flip over to our Kubernetes cluster, kubectl get kubectl API-resources. And that will list all of the things. So we can see the pods, nodes, bindings, component map, config map, endpoints, limit ranges, namespaces, nodes. And that is the list of all of the things. Some of them have shortcuts, like persistent volumes has a shortcut PV. Pods has a shortcut PO. Services has a shortcut SVC. Not all of them have shortcuts. But what we're after then is this first name. We want to list all the things. So we could say kubectl get pods and services and ingress, and it would list all of those things. So what if we could create a list of all the things and then concatenate that together? And that's this GitHub link. That was their answer to this. If you really want to get all the things, do this big kubectl API resources, pipe it to awk to go grab the first argument, pipe it to grep-v name, pipe it to zargs, pipe it to z-es, remove the spaces, and put in commas. And so now I end up with this list of comma-separated values, which is all the things. And the reason that I do that is if I include custom resources in my Kubernetes cluster, I also want to list those. And so now I have that comma delimited list, and I push that to kubectl get all, and then I have all of the things. Yeah, that's kind of a pain. So as we talk through all of these stateful things, you'll then say kubectl get all, and you won't see them. Bummer. OK. So the punchline, many of the things we'll see today aren't in kubectl get all. A bummer. OK, first stop in our stateful journey, volumes. Now in Docker land, I just say, hey, I would like to create this volume. I want to attach it, and life is good. I can either choose to make that persist into a store that I want, or I can let Docker manage it. And we'll see a similar mechanism here inside Kubernetes. I'm after file storage. Where do I store files that I want to upload? I could choose to use this to share between pods. Maybe I want to have that place where I'm uploading all of the profile pics. Or I may choose to just make it durable storage. Here is the place where I'm storing that backend database file. Now, the bummer part with volumes is that file locks don't work. And that kind of makes sense, because a file lock is specific to a machine, and this is a symlink off to somewhere else. So it's a file lock specific to my container, not a file lock specific to the data store. So a second container connecting to that data store is going to get a file lock on its machine, but not on that data store. So it's possible, if I mount the same volume into two pods, that I could overwrite the same file by accident. It's common practice for us to create different volumes for different pods to try and keep that separate. OK, so how do I do this in Kubernetes? Here is a pod definition. And this, I could choose to make this pod definition separate, or I could choose to bake it into a deployment as the template. But here's that pod definition. And I've snipped a bunch of stuff out of the middle that is all of the verbosity of things. But what we'll say here is we'll have this volume mount. And this volume mount says, I would like to map this volume into this spot inside the container. Here's the path in the container where I want this to take effect. And then I'll give it a name. So in this case, the name is the volume. Quite original. Then down here at the bottom, I will list the volumes and where the actual data storage is. So in this case, outside the container, in my host, I have a folder called mount host path to dir, and that's where the data will actually get stored. So this path here is on my physical machine, and it gets symlinked into this path in my container. Volumes. So now the magic question, well, who owns the hard drive? Is this owned by the developer who created the pod definition? Is this owned by ops who owns the hard drive that it's stored on? How do we kind of share this responsibility across this dev and ops boundary? Well, the cool thing is that Kubernetes has a really elegant abstraction here. It's a smidge involved, but let's dig through it. We have our storage, our hard drive. And then we'll carve that hard drive up into pieces. Let's call this a persistent volume. So each piece is a persistent volume. And then as I create a pod definition, I will check out one of these persistent volumes. I will claim that volume to be attached to this pod. And then I will reference that persistent volume claim in my container as a symlink. So we have our storage. We have persistent volumes. We have persistent volume claims. I'm claiming one of those volumes. And the persistent volume claim is attached to the pod. Now, what's really elegant here is that this creates a really nice separation of duty. The physical storage and the persistent volumes can be owned by ops. The persistent volume claim and the container can be owned by devs. And the only thing that needs to match is the persistent volume claim just says, I need one of those. Ops can continue to manage how it is stored and ensure that it's backed up and persisted in all the ways that it needs to. And developers can ensure that they have durable storage in their containers, but they don't need to worry about where it's stored. They just need to know that it's available and it's attached to their container and everything's working. Storage to persistent volumes to persistent volume claims to a pod. Any questions there? So this creates that elegant separation between dev and ops, and we'll see similar abstractions as we go through other Kubernetes elements. We have the ops side of things that allows ops to lock down the actual persistent storage, and the dev side of things, which allows them to just claim one and hook it into where they need to. Trying to get dev and ops to agree on what is this path. Is it path in container? Wait, did you typo container to dir? Wait, that wasn't the file. Oh, we upgraded it. Now the path is different. And that's why we have this separation where ops can own this side and devs can own that side.
There's an assumption in here that I guess it's all file instead of block I/O, right? Like Kubernetes doesn't know anything about blocks, so it expects to mount point to a file system it can talk to.
Right.
In that kind of going back to that, possibility you could overwrite a file from two different workloads, the same thing. Well, why don't you use a backend that implements a locking file system for you?
Yeah, good call. This isn't locking. So if I mounted that one persistent volume into multiple pods at the same time, and I didn't keep track of which files I was writing to, I could do really bad things. It's then typical that I wouldn't check out one persistent volume for all the pods, but I would check out one persistent volume for each pod, and then the pod would have their own folder, and now they wouldn't worry about overwriting things. Or inside that persistent volume, I would have folders per pod, or perhaps folders per application. Or my application is a write-only thing, so maybe overwriting things isn't a concern within the use case in my application. It's a fragile assumption, but it is an assumption. Yeah, why wouldn't they fix the locking? Yeah, why wouldn't they fix the locking? Apparently, locking across networks is hard. Distributed transactions are hard. That was a great question. What other questions do we have right here? Yep.
Worried about running out of space on like the physical storage stuff.
Mm-hmm.
Are there limits on each one of those volume claims that we can dictate so that devs don't spend more? Because these are all the bigger issues.
Yeah, good call. So I have this storage volume, and it's only yay big. Yep. It's only yay big, and so I'm checking out persistent volume claims. What if my pod overruns their space? Can I limit that to a certain amount of space so that I don't overrun? Did that restate your question?
Yeah.
Awesome. So let's dig in. Here's a persistent volume. Here in this persistent volume definition, I'm saying I would like this persistent volume to be, in this case, 10 gigs. That's the size of this drive. If you want a persistent volume, you will get one that is 10 gigs, and it will work in this way. At the bottom, here's the path where it's actually going to get physically stored. But to anyone consuming this, this is just a 10 gig drive. Now, it may be on a 4 terabyte drive, and so I have lots of these 10 gig partitions, but it is only 10 gigs. So yeah, I have however many 10 gig slots across my drive. But whoever uses this, they're going to get a disk full message if they try and write 10 gigs and 1 byte, in spite of the fact that the rest of the drive may have plenty of space. So that's that persistent volume. As an ops person, I'm defining how this volume works. I'm defining where it's stored. In this case, it's read-write once, which means only one pod can connect to it. And here's the actual physical path where it's stored. Yep.
So what happens when your app, let's say one pod uses 10 gigs, and when you first scale it out, you only have 3 pods. Great, awesome. But then you scale it up to 3,000 pods, and you consume all of the available storage. Is it hard provisioning those 10 gigs, or is it thin provisioning, or is there any control of that?
Good call. Can I over-provision based on I think that they won't all use the 10 gigs? That depends on your storage provider. And so in this case, I chose the host path storage provider, at which point it's just consume the hard drive until it's done. But I could choose to carve up my SAN, or I could choose to have it backed by S3, or something like that, where those rules are dependent on the constraints of the underlying platform. And by the way, I can plug in lots of other vendors' pieces that could handle that differently if the assumptions that I've chosen are no longer sufficient. Yeah, good call. Over-provisioning is fun. We over-provision with virtual machines all the time. OK, so here's my persistent volume. Here's the ops side of it. Now let's flip over to the persistent volume claim, the dev side of it. Now here in the persistent volume claim, I say, I would like a drive, and I'm going to only read and write to it once by one container. And I would like my storage size to be 3 gigs. So I have this persistent volume claim. I would like a drive that is at least 3 gigs. And it reaches out to the persistent volume, and it says, oh, I have this open 10 gig volume, and it happens to meet exactly your criteria, so I'm going to give you the 10 gig volume. You only asked for 3, you got 10. That's fine. I still have the 3 that I wanted. There's also a mechanism for creating a storage class, which will automatically create the persistent volume to exactly match what you asked for. And so that could be a really elegant way to pull in the pieces that you exactly wanted. But here's that persistent volume and the persistent volume claim. So the persistent volume lives over here on the ops side, and the persistent volume claim lives over there on the dev side. And the devs can say, I need at least this much, and ops is able to provide that content. That creates a really elegant, and so then how do we hook that into the pod? Here's our pod definition. And so we just say down here in the bottom at the volume section, the top as we're mounting the volume mounts, that's exactly the same. But down here at the bottom in our volumes section, we're just going to say, hey, this persistent volume claim is named PV claim. And because my persistent volume happened to be named PV claim, that's how I know that that's the persistent volume claim that matches this pod. OK, so I've gotten all the pieces, and now I have storage onto physical drives. As my pod restarts, it's going to reconnect that hard drive. It's still going to have all of those files available to it. Yep.
Thank you. I thought you had shown a slide that had 2 file paths in it, and then I was seeing the different configs that each had 1 file path in them. Like the talk yesterday, where we looked at one config can live within another config. Is that what we're seeing here?
Yeah, good call. So yesterday we saw a pod definition that lived inside of a deployment. And so all of this piece would live inside that deployment, inside that template. And so it's just as I'm defining this template, this pod, and that's probably the way I would do it, is I would put it inside a deployment. Here's that pod definition, and it's going to reference all the things. It needs to mount this into this directory inside the container. And where it lives on disk is right here inside that persistent volume. If I chose not to separate the dev and ops type of environment, then here's where it is inside the container. And here's where it is on the physical machine. But this whole pod definition could be inside of a deployment, or it could be as a standalone pod. That was awesome. Thanks for helping us tie all those pieces together. What other questions do you have right here? Yep.
Hi. Quick question. Is it possible to share a unique socket using persistent volume?
Is it possible to share
a unique socket across multiple pods on the same host?
Yes.
Or would you do that?
Good call. So how do I share? In this case, I said read write once, which means only one pod could get to it. But I could just as easily say read write many, and then lots of pods could get to it. At that point, yeah, all the pods are sharing the same physical portion of the disk. That's where we get into interesting problems with write locks. Yep.
If I get it right, Is it that physical, is it that physical volume is going to be persistent there no matter if the pods exist or not? It's like, is it like persistent forever, and then other pods, when they spin up, can still share it?
Good call. So I've carved out this piece of the hard drive, and I've attached it to the pod. Well, what if the pod goes away? Will the hard drive stay? I can choose to set it either way. I can choose to say this is temporary cache storage, and so when the pod disappears, feel free to blow away the volume. But by default, I'll have it persist. I'll say, I want that persistent volume to live forever, and whichever pod happens to claim it, they get access to it, and they can do what they need to do. And so it'll be based on that name. I have this persistent volume claim named PV claim, and so it'll get back to that storage. Good call. OK, so I think we've probably beat up persistent volumes real well. Config maps. How do we do configuration inside of Kubernetes? All of these things should be stateless and should be identical between environments, but we may actually have differences between our environments. I need to connect to the prod database, not the dev database. Config maps. Here's that spot where we store configuration, and it is, for the most part, a key value store. And that key value store is now specific to my application, so we could grab that from Key Vault or do interesting things, but in this case, we will mount it either as environment variables, or we can mount it as files with all of the details of our configuration. So here's a pod, and here in this pod, I'm going to say, I would like to set some environment variables. Now again, this pod could be part of a deployment, the template section of a deployment or a standalone pod. But here in this environment section, we're just going to list out the names and values for all of the environment variables that we want to set. So now, who owns those? Should ops own these? Should dev own these? Well, ops doesn't really want to share the credentials to the production database with developers. So again, we have a similar mechanism where we can separate those details. Here's a config map. And in this config map, we can specify the data that we would like to store. So here's that data section. And inside that data section, we can just kind of list the variables that we would like to use. In this case, I said database is memSQL, logging is true, the API URL is this. Those are the secrets that I want to use inside my application. And then in my pod definition, I can grab that config map right here. Instead of listing the environment variables, I just say my environment is from the config map named the name of my config map. It will pull in the config map. It'll pull in all of the secrets from my config map. And now all of these are made available as environment variables to my pods. Now here's the way where I can do it as environment variables. I could also choose to mount them as files. And so in this case, I'm going to have a volume that is mapped from a config map. And the cool thing is now in my path in container to dir, in that folder, there will be a file for each of those secrets. I can go read that file, and I'll get the latest value of that configuration detail. So now they're not just kicking around as environment variables within my container. I actually have to know that they're there, and I have to go read them. Maybe I'll put them in Etsy secrets, or maybe I'll put them in whatever directory makes sense for my application. I can then go read it, and I'll get the value of that configuration.
A value in the config map, will it get propagated out to the pod?
Good call. If I edit a value in a config map, will it end up in the pod? It will. It's magic. It's like really cool. If I've read that file previously and I've saved that value in my application doesn't know to go read the file again, though. So you do have to go check the environment variable or reread the file. That was awesome. I restated the question before the question. On the way to the question, that was pretty sweet. Okay, so some of our configuration is secret. Yep.
Back on config map, is the master or the etcd or whatever it is above the pod level maintaining the state of all these config maps for all services that are running in the cluster?
Good call. So etcd is the database that keeps track of all of the particulars of Kubernetes. Is that the thing that's storing all of these configuration details? Yes, exactly. In the same way that I say kubectl get all, or kubectl get pods, and it lists me all the details of each pod, I can say kubectl detail the particular pod name, and it'll list all the details of the pod name. I can say kubectl get config map, and it will show me all the config maps. Or I can say kubectl describe a particular config map, and it'll show me all of the details that I put into that config map. All of that is stored in etcd.
Can you use namespaces to isolate config maps?
Good call. Can I use namespaces to isolate config maps? Yes, I can. As I include this, as I apply this config map into Kubernetes, it's applied into the namespace that I've specified, either in my definition here, or probably in that I've specified on the command line as I apply that YAML file into Kubernetes. So that begs the question, so all of this is just kind of stored in etcd. But the credentials that I needed to connect to the database, I'm not really thrilled that they're just kind of there for anyone with a kubectl that just wants to pull those off. I want to store these secrets more secret. So we have secrets, and with these secrets we can do some interesting things. We may choose to store connection details to external services. We may choose to store API keys and secrets here, and all of this is encrypted at rest inside etcd as of Kubernetes 1.13. That isn't that long ago. Before that, it was encrypted as base64 encoded. Oops. I was waiting for the CVE that pointed that out, but no, it wasn't a CVE. They just chose to encrypt it at rest now. So yeah, how secret are they? If you can get them off into a key vault, they will be more secure. But now your application has to know to read the secrets out of the key vault. So this is secret-ish. OK, so how do I create these secrets? In this case, we're not going to use a YAML file. We're just going to define these inside of kubectl command, because to put it in a YAML file, we have to pre-base64 encode it, and that's hard. So kubectl create secret. Here's the secret name, generic, and then here are all of the keys in there. I want this in the generic secret thing. I'm going to create a key called db connection, and I'm going to use the literal from literal. So I'll say username equals dev user, and password equals password. And now I've stored these secrets inside that secret object named db connection. Now in my application, when I go look for, what is the db connection, I can get at that username and password and be able to connect to my database. So that's how we've defined the secret. How do we consume the secret? Similar in the way we map environment variables or volumes. In this case, we'll map it as a volume. And so I just reference that secret down here at the bottom, and it will then pull in all of the keys and values that are part of that secret, and they're available inside that folder. So my application can then open up this path in container dir. Inside that directory, it'll find a file named username. It'll find a file named password. It can open up each of those files and get at the actual data that is that secret. Alternatively, if I want to do that as environment variables, I definitely can as well. Here's my pod definition that may also be part of a template. And down here at the bottom, I'm just going to say, instead of defining the environment variable straight away, I will say the value is from the secret with this name and key. And it'll be able to pull those in as environment variables, and they'll just be available to my application. So in a similar way, ops can create the secrets, and dev can just reference those secrets, and away we go. Is it really that time? It is really that time. That's cool. So we're going to cruise through stateful sets at light speed. If I have a cluster of machines that need to talk to each other in interesting ways, I may choose to have a stateful set that gives them the predictable names. For example, a Kafka cluster, or an Elk stack, or maybe a database. Here's how that works, is I'll have each of these pods, but instead of getting random names, they will get specific names, pod-0, pod-1, pod-2. And Kubernetes ensures that I create the next one in sequence only after the previous ones in the sequence already exist.
This clock goes to 12:30.
This goes till 12:30, not 12 o'clock. Ah, I will slow down a bit, thank you. So stateful sets are awesome. What did I miss back here? Because I have this stateful set, now I can get these machines as very predictable names, and I can start to communicate between these machines with predictable names. Well, you can think of this as a deployment, but a deployment that creates pods in predictable names in very specific sequences. So some example use cases, database, Elk stack, Kafka cluster, those are all kind of great examples of when this technique would be useful. And here's kind of how that works. So I start off, the first pod that I create from this stateful set will be the name of my stateful set -0. Inside that pod is the container that was created as part of that. I'll create another pod in the stateful set because, I said replicas equals 2. The next one is called stateful set name -1. And if I said replicas 3, it will then create a third one, stateful set -2. So now I have 3 pods in this stateful set. And I know that they are -0, -1, and -2. With that knowledge in hand, I can create a headless service over the top of it. And this headless service then allows me to communicate between the pods. Pod 0 can reach out through the headless service to get to pod 1, or reach out through the headless service to get to pod 2. Similarly, incoming traffic can just get routed to whatever pod they needed to in the way normal services work. But this headless service, I must create the stateful set, and I must also create that headless service to be able to allow communication between the pods in a stateful set. So here's an example of that stateful set, and it looks a whole lot like a deployment, which is really cool. Here in the spec section, I'll create my selector that identifies the labels that I'll use to match into those pods. In this case, I said replicas is 3. I would like 3 pods in my thing. And then here's that template, that pod definition that defines how my template is built. And for the most part, everything under there is just normal pod stuff. Now, I may choose to also put in volume details or environment variables. Typically when I have a stateful set, it's because I want to store state. So all of the volume rules still apply. I'll want to check out a persistent volume as a persistent volume claim and connect that to the pod, but I've just kind of snipped that out. We're focusing on the stateful set. The major difference here from a regular deployment is that it is a stateful set instead of a deployment. For the most part, after that, it's just a regular deployment. Is it possible to create, is it possible to make the replica number match the number of pods in my cluster?
Nodes.
Oh, the number of nodes. That is interesting. So that I'll have one stateful set pod on each node? Yes, that is interesting. That is, it's not a stateful set, it's a domain set? Yeah, it's a domain set, which is exactly that, kind of a superset of stateful sets, but it ensures that it is one per node. Yeah, thank you for that. Yep.
Daemon sets ensure the same properties about like pod naming than daemon sets, than stateful sets, sorry.
Oh, good call. The pod names in a daemon set?
Yeah.
I'm not quite sure. I believe that they're random or specific to the node name. But you know, ultimately, when I'm creating a daemon set, it's like, I don't care. Just be available. OK, so I've got this stateful set. And I also need this stateful headless service. Now, what makes it headless is really interesting. Here, when I say cluster IP, I'm going to say cluster IP is none. Don't create a cluster IP, which is kind of cool, all else being equal. I like not having a cluster IP here. But this is the service whose selectors exactly match the details of the pods that I created. So here's those pods, and the pods have these labels. And so the service has these selectors that exactly matches it. That's how it knows which pods to put into this service. Now the cool thing then is as we're creating connections between each of the pods, down here at the bottom, I'm going to say curl the db-1.db-service. So I've created that headless service called db-service, and now I'm going to reference the pod 1 in that service. So now I can communicate with exactly that machine using a very precise, very well-known name. If I'm outside the cluster or I want to get to any machine, I can just go to db-service, and it will go across, it will use that same load balancing like mechanism. So we have this really cool DNS resolution inside that service to be able to get at the exact machine that I need to do. So all of the instances of my database can now communicate with each other and understand if the master is up, is the data shard available, and be able to balance my database based on the availability of the pods underneath it. Any questions on stateful sets?
Kubernetes wants you to define the headless service first before you define a stateful set with we call it selector that references it.
Good call. So should I define my service first, or should I define my stateful set first? I always like to define the services first, just so that as the pods start up, they can DNS reference all the things. But that's my preference. I don't know if there's a specific limitation in stateful sets of having to do the stateful set first or the service first. The tutorial that they walk us through actually creates the stateful set and then creates the headless service later. So I'm thinking it might not matter. I could also be really wrong.
Probably better though.
Yeah. I always create all my services first so that then I have the DNS names available in all of the pods before they start up. Good call. Yep.
Assuming that you'll have the database in within like inside the cluster. But what about like RDS hooking to something that's physical that's already there?
Right. Good call. The nature of stateful sets assumes that I have my database inside the cluster. But what if my database is outside the cluster? What if it's, you know, a database as a service or an external RDS? At that point, I'd probably just use a secret to connect to whatever that database is over there, and I don't need to work with stateful sets at all. Good question. So we saw stateful stuff inside Kubernetes. We saw how our application is more than just these stateless things. We still have ingress going to service, going to pods, load balancing across them, but we also have interesting things. Here's some config map stuff happening to be able to know what the domain is. Here's probably a secret to get the actual certificate in place. Here's some more secrets talking about the connection details to the database. Here's some more config maps that may talk about how to find that data store. The file storage will use persistent volumes and persistent volume claims to be able to create this durable storage that can persist beyond the lifetime of each of these pods. And I may choose to put my database cluster inside Kubernetes using stateful sets and a headless service, where I can ensure that each of these machines is persisted in a durable way. Now, these may also reference volumes and persistent volume claims, and perhaps config maps of how to get to and authenticate to those volumes to be able to store the state in my stateful set. What's really cool is Kubernetes originally was designed to be this stateless mechanism for hosting anything. But it's also equally sufficient for storing stateful things using config maps, secrets, volumes, and stateful sets, and daemon sets. Any questions? Thanks for coming. Good question. What tool did I use to build my slides? I use Reveal.js. The beauty of Reveal.js is that it creates a website. This website is available on your phone just as easily as it is here on screen, and so you don't need to download PowerPoint Viewer to do it.
Check 1, 2. Anybody in the AV NOC able to come to Ballroom B?
Test 1, 2. Can you hear me? Okay, good. I think we'll wait a few minutes for more people to show up. All right, so it looks like everybody who's going to be here is here, so right, let's get started. Today you are here for a quick and dirty introduction to Git. But first, credit where credit is due. This presentation is largely based on Alan Ott's excellent Git Like You Mean It presentation from SCaLE 16x. Heavily edited for time constraints. I urge you to view his presentation because he delivers it much more eloquently than I can even hope to. So, who am I? If you ask my private brain care specialist, he's just his guy, you know. Seriously though, my name is Donald Burr. I have been working with technology since, I don't know, like I was three years old. And my parents used to love it when I took apart everything in the house and usually not successfully put it back together. I've been working with Linux and FOSS software since the bad old days. My first vivid memory is sitting with a friend in his cramped apartment installing Slackware from floppy disks. And there was an insane amount of floppy disks. I forget how many, but yeah. Fun times, fun times. Mac Windows, Linux, GPL, BSD, not even going to go there. Just use whatever is the tool that suits you the best. That's what I say. And finally, I am currently a senior software engineer at VCT Labs. We're a small consulting outfit in Santa Barbara. We do just about everything. Check out our website, which is in need of work. That's my next project. And I apologize if I don't make eye contact with you because I am extremely nearsighted and I just squint down at my computer, so it's nothing personal. All right, so overview of SCM, aka Source Code Management. It encompasses the tools and methods for doing revision control of software. Generally speaking, you're talking about a centralized repository, which is sort of the authoritative source. Developers commit source code changes to that repository. A log is maintained of all changes, and branching and tagging is supported. And the central server is usually the authoritative source. The systems that we're probably familiar with the old way are CVS and Subversion, which is most definitely a centralized model. Your repository exists on the server. Each user has a working copy that they check out. They commit changes from their working copies to the server, and the history is maintained on the server. Well, this is great. It's easy to understand, classic client-server, but it has some disadvantages. It's very hard to preview commits. So once a commit is made, that's it, they're immutable. So if you screw up, well, usually you have to make a second commit. Oops, forgot X, you know. And anything involving the log must fetch everything from the server, and it's really, really, really slow. More drawbacks, any kind of branching or merging involves going to the server. Again, really, really slow, and there's no concept of local branches. And switching branches in particular is also very slow because you have to go up to the server and pull down whatever branch you're switching to. Merging is very difficult, varies by system. It's been getting better, but it's still pretty onerous. And finally, Subversion in particular lacks the support of tags. Instead, most developers do this sort of convoluted system. They create a directory called tags, and whenever they want to tag a release, they literally copy the entire stuff into a named directory in the tags directory. So it's pretty kludgy. Now, distributed SCM. It's a distributed system where each user has a full copy of the repository, including all the history, tags, branches, the whole enchilada. And when you're what's called clone from the remote repository, both the remote and your new clone start out identical. All the functionality of the remote repository is available on the local repository. You can make local branches, you can tag stuff locally, you can commit stuff locally, so on and so forth. And a local repository can even track multiple remote repositories, which we'll get into more later. This is great. I can commit code while I'm on the train. That's true, but believe me, it's just the tip of the iceberg. This is great. I can look at the log. I can look at the log while I'm on the train. Also true, but I mean it's just because looking at the log can be done offline. It's fast and much more useful, even when you're not on the train. This is great. I can create, switch to, and merge branches. Well, maybe I should move closer to work. It's not really about the train, really. It's about all the other implications of being able to work locally. What are they? Since history is convenient and fast, there's potential for history to actually be useful. If history is going to be used, it's important that history be clean. First of all, linear. You don't want one commit to depend on a later commit, because if that case happens, then the earlier commit is broken. You also want concise commits, germane to one thing. You don't want one commit that adds like every single 5 new features. I call them kitchen sink commits. They're pretty gnarly. How do we create this? Well, let's look at the old way. SVN and CVS, all commits are final. The documentation says Well, if you need to change something, just make another commit. Done. Well, it works, yeah, but wouldn't it be better to just get it right the first time? And CVS and Subversion does not contain a mechanism for that. So let's see some examples of the badness. Okay, so, all right, so commit 612 up here. Integration fixes from redacted facility. Well, that indicates to me that that's one of those giant commits that includes like just about everything under the sun. A kitchen sink commit. Well, yeah, that's a big mess. Then if you look at these down here, these two commits, bump version 2352, exact same commit message, probably means that the second commit up here is because I forgot something and had to add it in a second commit, but that means the first commit is likely broken. Another example of that here in commit 448, updated version 124, and then right after we have a commit, oops, yeah, commits with too many things combined, and oops commits bad. And more limitation. When you commit, committing code in Subversion's SVN commit, file 1, file 2, blah 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 blah. What if you forget one? What if you have some debug code in there that you don't want to commit? What if you screw up the commit message? There's really no way to go back and fix it. You have to do one of those oops commits. So how does Git handle this? Well, in Git, we provide tools to address these issues. Local history is editable, which means once you commit something, it's not quite set in stone until you push over back to the remote repository. You can feel free to edit, fix things, and also Git has a separate add and commit procedure. Means it's easy to review what's being committed before you actually commit it. This means you can do small atomic commits, and it means it's easy to create a linear history, where one commit doesn't depend on a future commit. And if you mess up, you can go back and fix it. And once you're satisfied that it's all right, then you push it off to the remote repository. So, great, we can clean up the history, we can, who really cares, who cares? Well, you should care because it makes small, clean commits make code review possible. It means you can have problems are harder to introduce, there's fewer unintended consequences, and it also makes bisection possible, which is really cool, and we'll talk about that later, time permitting. And all of the above contribute to better code quality. So, let's talk basic Git tasks. To create a Git repository, go into your source directory and run the command git init. Creates a directory .git. That's where the actual repository stuff is. The actual files in the current directory are your working copy. And when you created a repository, no files are committed automatically. You have to do that yourself. To add files, just git add file spec. You can use wildcards, whatever. This adds a file to the index. Git has three sort of working areas. There's the working copy. That's the directory where all your source code that you're working on lives. There's the repository where all the Git stuff lives. And then there's this zone in between called the staging area. I like to call it code purgatory. It's where your commits go and wait it's where when you add files to a commit, they just sort of go there and sit there until you're ready to commit them. Yeah, so when you add a file, it's not committed, but it's staged for commit. Git add can be run multiple times to stage commits from multiple files for a single commit. And to actually commit it, you do git commit. This creates a commit containing all of the changes which are in the staging area. It'll open your editor to ask you, you type in your commit message, blah, blah, blah. And once you save and quit, it's committed. After running the previous command, your repo has a single commit. You can view your commits with git log. This opens up the log in less. You can use up and down arrows. You can scroll and press Q to exit. You can also view the diffs that each commit contains if you give the -p argument. After the initial commit, you'll probably change and add code, do normal development. At any time, you can show the status of the working directory using git status. It shows any files that you've added, changed, or removed. It shows any conflicts if they exist. And it also shows any files that are staged for commit. To show everything that's been changed in the working copy, do a git diff, and this shows a colorized diff, and you can page it with less. It's really cool, really handy. At some point, you'll have multiple commits worth of stuff in your working copy. You've been hacking on code for a while, and you fixed 3 or 4 bugs. You've added some things, so you have a bunch of changes in the working copy that you want to commit. But again, you want to try to keep your commits small and germane. So you can actually stage individual changes in each file using the git add -p. This will literally go through all your files that are changed. It'll show what you changed, and it'll ask you what to do with it. Do you want to stage it? Do you want to not stage it as part of this commit, and so on and so forth. Once you've added all the diff chunks for a commit that you want, once you've added everything that you want in that commit, you should review them using git diff -cached, which shows the difference between the repository state and what's in the staging area. This will show you all the changes staged for commit. It's important to do this review. Sometimes you can confuse yourself. Maybe you added something that you shouldn't have. You can always go back and fix it. And if there's something you don't like, you can change it. To make the change, you can actually change your working copy and then run git add -p again, and it'll update the index or the staging area. To remove changes in a file, you run git reset head and the file name. This basically removes all changes from the file name. This basically removes all changes for the file name from the index. Once you've reviewed your changes, you can commit them with git commit. This will create a single commit. It'll pop up your editor and ask you for a commit message, which we'll see in a moment. Now that you've made a commit, run git log, and you'll look at it. You can see it. Make sure it looks the way you want it to. And it makes it easy. Your commit message will be indented by 4 characters. And of course, checking your work is always important. So if the commit message is not right, maybe you made a typo, maybe you left something out, you can easily change it with git commit-amend. This will edit the log message of the topmost commit, which is called head. And other commit messages, you can actually change other commit messages as well using rebase, which hopefully we'll get a chance to get into later. So you made your first commit. Run git diff again to see the remaining changes and iterate until finished. Lather, rinse, repeat. To get more information, you can always do git status at any time. This will tell you changes in the working copy, changes stages for commit, and how to revert changes if that's what you really want to do. Commit messages, Git has a de facto standard for them. The first line is the summary line. It's always displayed. There's 2 ways of viewing Git logs. You can either view the full log, or you can do what's called a one-line log. And if you look at a one-line log, all you see is the first line. So that should be basically a concise summary of what that commit contains. And there's sort of a de facto standard for them. You put the subsystem, whatever subsystem that commit affects, followed by colon, and then a short description of what the commit entails. follow that with a blank line, and then you can put in a longer description. And when I say long, I mean long. You're not really limited in any form other than disk space, which is plentiful. This is a great place to describe in excruciating detail what your change, what your change is about, and it's great for documentation. If I'm working with coworkers, like in a Slack or something, a lot of times I paste in the Slack logs. It's really cool. And when you're talking, you really should use the imperative mood, which is basically commands. Change X, add support for Y, handle exception in Z or Z, depending on your nationality. Don't use sort of the, this patch does this. It's that whole sort of passive voice thing that your English teacher drummed into you. So here's a sample commit message. The first line is the SHA-1 hash of the commit. It's basically a hash of everything in that commit: patch, date, time, author, email, blah, 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 including the hash of the previous commit. This commit ID serves as a unique identifier of this particular point in the history. It identifies the specific commit, and since it also includes the hash of the previous commit, it also identifies indirectly the branch that this is on. The commit ID is used everywhere in Git where it asks for a revision, and you'll see that in the Git documentation. A lot of commands ask for revision as an option. Well, that's you can give these SHA hashes, and you don't have to type in the entire long hash. You just need to use enough characters to where it's unique across that repository. In general, usually using only the first 6 to 8 characters is fine and a lot easier to do. You can also use it with git checkout to check out a particular point in history. So git checkout the hash or whatever. It'll check out a specific version to the working copy. Next, we have the author and the date. One particular note is that the date shown here is the date of the commit, not the date that it was merged or pushed to a remote repository. So that means new commits can potentially have old dates. So dates are not necessarily increasing, and commit dates are not a good way of determining the state of the repository on a particular date. Next, we have the summary line. Again, the summary line and the long description. Again, subsystem : brief description, and then a blank line, and then go hog wild. And I have a formatting error. Oops. So yeah, you can definitely put more info in the long description, and more importantly, you can reference other commit IDs in that description. And in many cases, like if you're looking at a repository on an online service like GitHub or GitLab, they will turn those into clickable links so that you can just literally click and see what commit that you're referring to, which is pretty cool. So, the interactive demo, I'm going to defer the demos until later. Hopefully we'll have time, but if not, check out Alan's presentation because he goes into exhaustive detail. All right, now let's talk about ranges. Some Git commands can take a range parameter. For example, you might want to look at the differences between 2 different commits. For example, git diff shall, and the way you specify a range is something ... something else. So that something can be SHA hashes, it can be branch names, it can be tags. We'll talk more about that later. This basically shows all the differences between the 2 revisions that you gave it. The same can be done with git log. It'll show all log messages. it shows a log of all the commits which are in that range. Remember, in general, ranges are older ... newer. Excuse me. You can also use symbolic names, meaning the name of a branch or tag. So, like if you have a release tagged as 4.13 and you want to, and 4.14, and you want to see the differences between the two, you can do that. One revision has a special name, head. Head describes the most recent version which is checked out in your current branch. And this is useful because sometimes you might want to get a log or diff from some revision to head. So, if you wanted the differences, 4.14 and head, that's how you do it. You can also reference a commit previous to a specified revision. Usually this is just done using head. So for example, putting a caret after revision gets the revision previous to the specified revision. So if you do git log head caret ... head, that basically shows the most recent commit. And you can use multiple carets to go even further back in time. So git log head caret ... head gets you the last 4 commits. That can be kind of awkward, so there's also another alternate syntax. You can do head, with a tilde and a number, which indicates the number of commits to go back. So git log head tilde 4 ... head is equivalent to git log head caret ... head. As a shortcut, the last revision can be omitted and head is implied. So git log head tilde 4 is the same as git log head tilde 4 ... head. And check out the man page for more information. Branches and merging. This is really important stuff. Remember that in a distributed SCM like Git, the entire repository exists on your workstation, which includes branches and tags. And that means you can make branches locally, which do not correspond to upstream. Branches are really, really fast to create and fast to switch between. Very convenient to create local feature branches where you can do work on. Git will always give you a default branch called master. Typically, this is the branch that's synced with the upstream. It's basically equivalent to trunk in SVN. There's nothing really special about the mechanism of master. Git's not going to enforce anything regarding that, but generally this is the sort of the de facto way of doing it. To view local branches, just run git branch. Whatever branch you're currently on will be indicated with an asterisk. To create a branch, you can do git branch name. Pretty simple. However, note that when you create a branch, you're not automatically switched to that branch. To do that, you use git checkout. So checking out a branch checks out the branch to the working copy. Working copy will contain the branch. The log will reflect the branch that's currently checked out. And when you commit, it'll be made to that branch. You can easily switch between branches using git checkout. Make sure to commit your changes beforehand, otherwise Git will complain. So it's convenient to use branches to work on a feature. Make a branch, check it out, work on, do work on feature X, commit your changes. Then when you're ready to merge those in, you check out master, and then you merge your feature branch in using git merge. Hopefully your branch can be merged. If not, Git will often tell you in great detail what needs to be done to make it happen. Sometimes you'll have conflicts, and conflicts work similar to how they work in CVS and Subversion. And hopefully I'll have time to get to the branching demo. Right. Now let's talk about revisions. So you can check out branches, but you can also check out other things. You can check out a specific revision, aka SHA-1 hash. You can check out a specific tag. You can check out branches. This makes it very easy to work with older revisions. When switching between revisions with Git, sometimes there'll be conflicts, and in that case, Git checkout will refuse to alter the working tree, and it'll warn you. Now, if you really want to check out that branch, you can do something called stashing. This is pretty cool. Basically, Git is able to store away all of your working directory changes into a sort of holding area called a stash. There's also hard mode, which I call the nuclear option, because it resets the commit history, but also resets the working tree. And be very careful with this, because if you have any unsaved changes, it will wipe them out. Hence why I call it the nuclear option. There's also Git reset soft, which it resets the commit history, but it leaves the changes and puts them in the index, basically in the staging area. And the man page for Git reset describes all of that in greater detail. Now, rebasing. And this is the concept that I found really hard to wrap my brain around for the longest time. But it's really powerful. Probably the single greatest feature, in fact. Remember that in Git, the history is editable. So this might seem scary, but really it's not. It's a huge benefit. Remember that your history in distributed systems like Git is local. So, that is to say commits which are not yet pushed to remote. You can usually edit local history before it is pushed to a remote repository. Basically, this is a way of getting it right before you send it off to the world. So what is rebasing? There's two kinds of rebasing. We'll first talk about simple rebasing. Simple rebasing involves inserting commits from another branch or upstream before your local commits. So, for example, you checked out some code, you've got a working branch, you've done some stuff, made some commits. Meanwhile, back at the ranch, someone else has pushed commits to the remote repository. However, when that happens, you want your commits to be on top of the remote commits. So here's a little example. The state before you started work just has a master branch. It contains the main line of development. It has some stuff, potentially fast moving. So you check out you create a working branch. This is on your workstation, and you make branch local commits to it. However, meanwhile, commits are made to the master branch, maybe from upstream, maybe from other developers, which means that master and your working branch now have diverged. And so if you want your commits to the working branch to go up to master, you might have some conflicts, and you'll have to work on removing those. That's what git rebase does. Basically, it pops your branch local commits out of the history and saves them. It applies the commits from master to the working branch and reapplies your saved branch local commits to the working branch. So the name is appropriate because it rebases your local stuff. So here's the basic workflow on that. You check it out, you do some stuff, and then meanwhile other people are doing stuff to master. When you're ready to you check out master and you pull from master, which means get the changes from the remote repository, and then you check out your working branch again and you git rebase master. And what it does is it saves all your commits, which are in the working branch, but not in master, to a temporary area. It resets the working branch to the most recent commit, which is common to both your working branch and the master. It applies all the commits from master, which are not in your working branch, and then it applies your saved commits from your working branch. Of course, this means you could come into conflict. Maybe you were modifying something that someone else did. In this case, rebase will stop and give you an opportunity to fix it. At this point, you can run rebase-abort, which cancel, and that basically reverts back to before your rebase attempt. Or you can fix the commit and run git rebase-continue. If a conflict or exception cases occur, remember that a lot of times Git will tell you what to do. And running git status is a good way of finding out what needs to be done. It basically, and one thing I find helpful is opening a second window. That way you can have one window where you're working on resolving the conflicts, but you have the second window where you have your status message, so you can always see what needs to be done. Really handy. And another demo, which I hope we'll have a chance to get to. Now, the second type of rebasing is interactive rebasing. So simple rebasing, which is what we just finished talking about, is used to integrate the history of one branch into another branch. History is rewritten. With interactive rebasing, it also rewrites history, but it's a lot more flexible. Remember, of course, that rebasing should only be done in local branches which are not pushed yet to remote. Interactive rebasing is really cool. It allows you to dramatically rewrite history. Of course, again, only do this on a local working branch. Do not rebase commits that have been pushed to a remote repository. Use rebase to integrate changes. One great use of interactive rebasing is to use it to integrate changes that were suggested during code review. And this can happen before a branch is merged to master. So rewriting history is important during the development process because, first of all, you want your history to be as simple as possible, meaning simple commits. You don't want those kitchen sink commits that include basically everything under the sun, like I talked about. You want to make commits linear. Each commit builds on a previous commit. Commits don't undo one another, and there's no oops commits. Just rebase and fix them. And again, your goal is to make every point in history valid. No commit should break the build. So to start, you run git rebase-I followed by a revision, which will rebase all commits newer than said revision. And when you do this, Git will open up an editor window with a list of commits, one per line. Each line indicates what to do with. You use the editor to specify for each line what to do with the commit and the SHA-1 and the commit message. From this window, you can delete a commit just by deleting the line. Be very careful because it literally will wipe that commit off the face of the planet. You can reorder commits, literally just moving lines around, copy paste. You can modify the commits. You can edit by editing the first word of the line. The file has a little comment section that tells you exactly what you can do. The most used commands, P for pick, which basically leaves that commit as is, which is the default. R for reword, lets you change the commit message. E for edit, lets you change a commit. And S for squash, lets you basically combine one commit with the previous commit. There are more things you can do. They're kind of, in general, used a little less frequently, and read more about it in the little comments section in the editor when you rebase. So easy to move commits around. Of course, there's a problem when you get a conflict. Again, it's just the normal conflict resolution stuff. You'll be able to resolve the conflicts manually. Be careful when editing the rebase command file. Deleting a line will literally remove that commit from the face of the planet. Again, I find it really helpful to have multiple windows for this, because in one window you have the rebase command file, or the rebase command line, because it'll stop either for an error or for editing, and it'll tell you the next steps. So I like to leave a window open for that, and then have a second window to do all your stuff, editing, resetting, all that. Splitting commits. Interactive rebase can be used to split a commit. So let's say you accidentally made one of those kitchen sink commits and you want to split it into more discrete components. Simply mark that line as E for edit, and the rebase will stop at that point. It'll reset the log to the previous commit, leave the changes in the working tree. When it stops, you should reset the log to the previous commit and leave the changes in the current working tree by using git reset head caret. So now that commit has been removed. So you recreate it in the way that you want, possibly splitting it up, breaking it up into multiple smaller commits using the standard git add-p and git commit lather rinse repeat. It's another demo. Looks like we might have some time. So, important things to remember: rebasing is destructive. Make sure you back up. You can always just create a new branch as a backup, or copy the whole repository. It works. Double check which branch you're on. It's so easy to be wrong. And know whether you're up to date. Make sure that you're up to date with whatever the upstream is at. All right, remotes. I'm going to go through this kind of quickly. Basically, we've dealt with the local repositories so far. However, Git supports remote repositories, and several protocols are supported. Git, HTTP, SSH, local file system. For remotes that you authenticate with, you'll often use SSH. And HTTP or Git is often used for anonymous projects. When you clone from GitHub, you'll see the http://github.com/blah whatever. And file system is good for cloning a repo that already exists on your local disk. Git supports multiple remotes. You can push and pull to and from each. This is because Git can detect when repos have a common history. Very easy since you have the SHA-1 hashes, or the SHA-1 hashes. Some example cases: the Linux kernel, public and private repositories. You have a code, you working on code from your own private repository. but when you want to send it off to the world, push to GitHub. So getting a repository from a remote is called cloning. It's git clone, blah, 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 whatever. SSH syntax requires the public key. Git protocol is anonymous. HTTPS protocol is useful if you're behind a firewall. These commands clone the repository, including all history from the master branch. Cloning a repo gives a single remote called origin. Other remotes can be added. Git add remote, symbolic name, URL. And you can check out branches from remotes. Git check out remote/branch. You can look at what remotes are being tracked using git remote-a. And when you check out a branch from a remote, it'll automatically track the remote from which it came. So if you do git push to send stuff up, or git pull to pull the latest down, it'll do what you expect it to. You can see what branches are available on the remote by doing git branch-a. There's clone with reference, which basically sometimes you might want to make a new copy of repositories that you already have. Use --reference to clone a local repository. It'll use hard links to save space, and cloning will be faster. Fetching remember that your local Git has the capacity to be a complete repository. You know, you can have your own branches, tags, etc. Git fetch will fetch all of the branches, tags, etc. called refs from a remote to your local repository. It will not modify your local copy or your working copy. Push and pull to get updates from remote. You pull from it. Git pull remote name and the branch. Or a lot of times it's implicit, you just do git pull. But usually it's best not to do it like this because, yeah, if your local branch has local commits, then your history will diverge from upstream, in which case when you do your git pull, Git will do what's called a merge commit, which is probably not what you want. Really, you're better off pulling with FF only, which means that only fast-forward merges are allowed. That means, this means that the local repository has no local commits. If it can't fast-forward, it'll just fail. Then you figure out why, fix it, and try again. And again, Git is usually pretty vocal about what's going on, so it makes it easier to fix. All right. Avoiding pull issues. Have your master branch that tracks an upstream. Do your work on local working branches, and when the upstream changes, check out the master. Do a git pull with FF only. Git check out your working branch and rebase against master. And now your working branch is up to date. Pushing is sending your changes, your commits to remote, most often the origin. And when it's time to push, git check out master. Make sure your master is updated from the remote. Then merge your working directory and push. Sometimes you don't have push access. Usually this is the case for open source projects. In this case, you'll send patch files to the maintainer, and Git makes this pretty easy to do. Git format-patch makes a nicely formatted patch file that you can send off to, to the maintainer. You can also it also makes cover letters, including statistics. Be sure and edit it before sending. And then you can then Git will even use your configured mail client to send it, doing git send-email. Pretty cool. If you're submitting upstream patches, see this excellent talk. And if you are the maintainer, you can accept patches using git am. This will append a set of patches into your commit history, and it does preserve the author name that's present in the patch that you got sent. Right, reflog. Reflog is something pretty cool. Git keeps track of when branches change, whether it's by commits, pulling, merging, whatever. This information is stored in the reflog. Each change gets an entry into the reflog, and the repository can be reset to that state. And the reflog is stored locally, it is not pushed. And to see it, run git reflog, shows all the entries and their SHA-1 hashes, which is a different hash than the commit hash, by the way. And to reset a repository to a previous state, do git reset. The reflog is great if you mess up a rebase or a pull, just reset to a known good state. It can be kind of tricky to find the last good state. Just be careful, pay attention to the messages that Git gives you. And most importantly, the reflog is not guaranteed to exist forever. It can be garbage collected at any time using git gc. And in some cases, Git can be set up to automatically run garbage collection. Yeah, don't depend on reflog, basically. It's there as a sort of an emergency safety net. Now we get to bisecting, which is super cool, especially on larger projects. I mean, you could have a few thousand commits go by before noticing, oh crap, X broke, or whatever. How do you determine where the bug was introduced? Git helps you with, it's this really cool thing called bisecting. Basically, it performs a binary search. So you give it a known good revision and then the bad revision, and tell it to start. And what it'll do, say this is the bad one, and this is the good. But I'll do it from your point of view. Say this is the bad revision. Say this is the known good revision, but this is the bad revision. So Git will basically pick a point in the middle and check that out. You build it, try it. If it's good, then you tell Git that it's good. If it's bad, then you tell Git that it's bad. So let's say it's bad. Well, that means that the bad change happened somewhere between the known good state and here. So then Git will basically take the middle of that. And it's basically binary search algorithm. And it makes it super easy to find where stuff broke. It's really cool. It lets you find the error in O log n, or O log squared n, where n is the number of commits. You can search 1,000 commits in roughly 10 steps. Super efficient and super cool. So to start, git bisect start, then give it a good revision and bad revision. Then Git will start the bisection. It gives you the center commit. Test it, build it. If it's great, if it works, say git bisect good. If it's bad, git bisect bad. Then it'll give you another commit to test. Lather, rinse, repeat. Excuse me. Eventually, it'll tell you where the first bad commit is. This is the one where the bug is introduced. When you do that, when you get there, run git bisect reset. It's a lot easier than it sounds. During a bisect, Git can potentially give you any revision in the history to test. And this is why it's very important that every commit build, run, and pass tests. I mean, imagine a situation where bisect gives you the commit before an oops commit. Yeah, that wouldn't be very fun. This is also why it's important that history be linear and older commits not depend on newer ones. Teamwork, a lot of, these are the tools to enable large distributed teams of developers to work together, rebasing, cheap local branches, multiple remotes. And this really gets started out because the Linux kernel developers needed a effective way to collaborate, and the Linux kernel team is probably one of the largest software teams in the world. So, this is a great a great example of eating your own dog food. Typical method, each developer has their own online repository. Developers work on code, push it to their own repositories. When it comes time to submit code to the maintainer, the developer uses interactive rebase to linearize and clean up their commits. Usually this happens on a new branch. Once the new branch has been rebased and is cleaned, the developer pushes to the branch to their own public repository and then sends a pull request, which isn't the same thing as what GitHub calls a pull request. Basically, a pull request is typically an email that says something like, "Hi, please pull from URL," and then the maintainer can pull this branch into their own local repository. They can look at the changes using the git log, and even if the developer's branch is based on a revision older than what's on the maintainer's master, it still works. In fact, this is probably the likely case. And of course, Git recognizes the common history and shows only the developer's commits. The maintainer will provide feedback. Developer can integrate the suggested changes using rebase-i, submit another pull request. Maintainer can then repull the branch, review, and merge. And the advantages, code review is possible. Code can be reviewed at the commit level before commits are actually made in the upstream master. Commits can be modified by the developer an unlimited number of times before merging, and this improves code quality. And of course, the maintainer has complete control of the repository, no surprise commits. Last thing I want to talk about today is branching methodologies. With all these great tools, you know, the old saying, with great power comes great responsibility. You know, you don't want to be creating branches willy-nilly, especially if you're working in a team. You want to settle on a standard for how you manage branches and tags. So, yeah, get your branching right. And I don't know why that's a blank slide. Okay, so. And I apologize that this is so small. In the links section that I'm about to get to, I'll provide the link to all this. So for traditional large software projects, fairly slow releases, this is a good branching model. Is this: you have a master branch, and the master branch is basically untouchable. You don't do anything on the master branch. You do everything on developer branch and on a developer branch, and you know, each developer branches off from the development branch, does a feature, you know, fixes a bug, works on a feature, whatever, merges back to the development branch, and periodically when you want to cut a new release, merge development into master, tag the release, boom, you're done. The only way that master should ever be touched is to have stuff merged into it. So that's great for large projects, but what about smaller projects like you know, web apps? Frequent releases, a lot of very much moving target. You don't need to get that complex. In fact, it's kind of counterproductive. Much simpler way is just to use master. You know, whenever a developer wants to fix a bug, add a feature, just branch off of that and then merge back to master. Yeah, so resources. Pretty much the Git Bible is a book called ProGit. It's available online. There's also a great website called Ready and man pages. Git has great exhaustive man pages, and to reference a particular man page, you use git-command. So for example, if you want to read the merge man page, you do man git-merge. Branching models, which I just talked about, those are the two. They have some really good articles on there. Integrating Git with Bash. One really cool thing is, that I find really helpful is, you're able to integrate Git with Bash. So for example, let me show you. So for example, here's one of my repositories. Notice I have whatever branch I'm on as part of my Git, my bash prompt, and then don't know why it's not working, but if it were working, Git bash integration also lets you do tab completion, but you can get that at that site. And finally, Alan's great presentation, the OG. There's a video and there's slides. And that's about it. And I think unfortunately my time is just about up. Check out Alan's presentation. Check that out. He runs through all the Git demos. It's pretty cool. Anyways, are there any questions? I think I have a few minutes. Go ahead. Yes. Every time you put a change in, depending on how you have configured the prompt for your password. Right. Unless you have flags in that configuration where you can tell not to do that. Yes. That was a real problem last time. I couldn't figure out how to stop the thing from popping. Yeah, there's a global configuration called .gitconfig, and one of the things that you can do in there is you can do set up what's called a key store, and that's a facility local to Git that stores your passwords and stuff, so you don't have to enter your password every single time. Anyone else? Go ahead.
Revising every single one of hundreds of old commits to fit this mold?
I mean, I don't know. It depends. If you're talking about a huge project, probably not. But I would definitely start adhering to the conventions from going forward. But yeah, for a large project, it might be a little more trouble than it's worth. Anyone else? I can't see you if you raise your hand, so. Go ahead. So the question was if you can tell who has their branch checked out. Is that was? And you can't, and that's one of the things to get used to in the distributed model. It's not like Subversion where when someone checks out a branch, it's sort of locked to them, which is kind of a pain. So yeah, there's no real way of telling who has checked stuff out. You just have to wait till the pull request. Anything else? All right, I think we're good. Thank you so much for coming.
Hi, is there a mic in the room? Any Michaels? No? Okay, this concludes the mic check.
Yeah, looks good.
So welcome everybody. Rob has chosen to restore having a service mesh talk on the schedule after our original Istio speaker had to cancel due to travel restrictions. And he's going to brief you on this. Just quick check, actually, did anybody attend the Linkerd talk next door before this? Okay. So you're going to have a few people, right? Well, so you know what they learned in the Linkerd talk.
Yeah.
We'll cover that. You know, and he's going to, you've probably, if you've been here for the whole conference, you know who Rob is. And he is going to explain to you service mesh. Take it away,
Awesome.
Rob.
Thanks for the introduction. So service mesh to service mesh. Imagine an uncontrolled roadway. Imagine there's no limits, there's no speed limits, there's no traffic lights, there's no signs. In a small town, this works out really well. In time, maybe this doesn't work out so well. So we've got that one county traffic cop who's standing at the edge of town with his radar gun, and he's going, you know, I'm going to improve this scenario. I'm going to stand at the edge of town, and anyone coming in who's not obeying the rules, I'm going to grab them, and I'm going to make sure that they obey the rules. In time, maybe we'll get more traffic cops, and we'll kind of spread them out throughout the town. And unfortunately, the net result is that we're enforcing conformity, but we're still not optimizing for the goal that we want to get to, which is to get from where I am to where I need to be as fast as we can possibly go, as efficiently as we can possibly go. And that's a great analogy for how service mesh kind of fits in this scenario. We can start with a cluster with services where anything can kind of talk to anything. And we can get to a scenario where we have very specific traffic patterns, and we can adapt to changes in our traffic patterns to ensure that we have a lot smoother roadway. Let's dig into service mesh. Here's the part where I tell you I'm definitely going to post my slides on my site tonight. You're going to hit my site tonight, tomorrow. You're going to be pushing refresh next week, next month. In about 3 months, you're going to get tired of checking. You're going to email me. And in about 6 months, I'll promptly reply and say, no, I'm definitely going to post these slides on my site tonight. Which is why you can go to my site right now, robrich.org. And as you go to robrich.org, you can scroll down to service mesh. And here is the slides that we're going to look at right now. They are online right now. While you're there, you can see some of the things that I've done. I'm a Microsoft MVP. I'm a friend of Redgate. AZ GiveCamp is wonderful. AZ GiveCamp brings volunteer developers together with charities who otherwise couldn't afford software services. We start Friday after work. We build software for them. We deliver that software Sunday afternoon. Sleep is optional, caffeine provided. Come join us in Phoenix at our next AZ GiveCamp, or if you'd like a GiveCamp in your area, come reach out and let's see if we can plant a GiveCamp in your town. Some of the other things that I've done, I worked on the Gulp team in version 2 and version 3 as a core contributor. I've written a book, SQL Source Control Basics. Mine is chapter 8. And I do training through getgrit.com. If you like what you see today and you want this in your organization, we can definitely make that happen. Come see me and we can do Kubernetes and Istio and Docker and all kinds of other interesting things in your organization. One of my claims to fame is I posted a comment on the .NET Rocks podcast episode. They read my comment on the air. They sent me a mug. Woohoo! So that is my claim to fame. So with me, except for not with me, is Kavya Perlman, my good friend. She helped me build this presentation, and she is an amazing person, a cyber guardian for WallArm. She originally worked for Facebook during the presidential election and got to see all of the wonderful and wacky things involved in security and all of the abuses firsthand, which was amazing. She then moved on to Second Life, where she was in charge of the largest online community, and that was amazing. She now runs the XRSI Foundation, doing security around virtual reality and augmented reality, and that is really amazing. So I'm grateful for her help in putting this presentation together. So what are we going to do? We're going to look at kind of what is a service mesh, kind of the history of how we got from to where we are. We'll look at both Istio and Linkerd, and then we'll demo each of those, which will be really fun. And we'll look at kind of service mesh best practices, when you might choose to use service mesh, and when this might be overkill, and when you might want to avoid it. So let's dive in. A service mesh. A service mesh manages the network traffic between services in a graceful and scalable way. Service mesh is the answer to how do I observe, control, or secure communication between microservices. That's kind of a decently crisp definition, and let's dig into a whole lot more of what that means. But at the outset, it's a way of managing communication between services. That is the service mesh. As compared to a mesh of services where I have all of my microservices communicating, a service mesh is the thing that controls the services. It does not replace the services. I still have my mesh of services. I just choose to control them with a service mesh. Arguably, the title service mesh is really awful for exactly that reason. It does not replace my services. It controls my services. So we want to talk about kind of the main principles of service mesh. Observe, control, and secure. And that's really the foundation of what we're going to do with a service mesh. We're going to observe traffic between containers. We're going to control that traffic, validating against policy rules and traffic rules. And we're going to secure that. We can use mutual TLS to ensure that communication between containers is secure. Observe, control, and secure. We'll come back to that about a dozen times. So how did we get here? Well, we started out with a monolithic application here on the left. And the monolithic application, we built all of the pieces into one deployable component. And we chose to deploy it as a monolith because deployment is hard. And so if we didn't have to do that very often, we could just, for example, deploy our monolith once every 6 months or once a year. Then we didn't have to go through that pain as much. Over time, we moved to virtual machines and eventually to containers where deployment was no longer a barrier. Because deployment is no longer a barrier, we could do it really frequently, like, say, 20 times a day. Now that we can deploy really easily, let's start splitting our applications into smaller, simpler components. So we end up with, for example, these 3 microservices. The user interface will route into the microservices. Each microservice then will route into its data store. And then we're able to kind of architect our application from these loosely coupled components that do really interesting things. So now we have microservices, but now we end up with a mechanism where maybe communication between the microservices is a little weird. So first, I'll talk about north-south and east-west, defining these terms. In this diagram, we talked about how the user interface goes down into the services go down into the... So north-south generally refers to into or out of the cluster, where east-west traffic talks about communication between components. So when we talk about north-south, that's into the cluster or out of the cluster. East-west is between components inside the cluster. North-south and east-west. Which is really funny because we have these north-south diagrams, and then we have diagrams where traffic moves horizontally in north-south traffic, and it's like, okay, you know, are we mixing metaphors by not doing the north-south correctly? That's kind of interesting. So let's add an API gateway. Here was our first step towards controlling the traffic. Much like that traffic cop at the edge of town with his one radar gun, an API gateway is a great boundary around your cluster. Content can't get into the cluster until it goes past the API gateway, and the API gateway says it's okay. But once inside the cluster, we have all kinds of strange stuff where the containers are talking to each other and a microservice is talking to another microservice's data store. We don't have that same symmetry where a microservice owns its own data store because that API gateway will only guard the boundary to our cluster. API gateways are great for guarding the boundary of our cluster, but that's all. They can also do some interesting things about payment and tracking usage and things like that. So it's not just about security. But primarily in the security space, it's just about validating the boundary of our cluster. Any questions so far? So we've got API gateways, and now we want to add a service mesh. Well, what is a service mesh? At its most foundational level, a service mesh will typically use a proxy to communicate between services. So for example, here's this service on the left, this service A. And service A would like to communicate with service B. Now service A typically would just open a socket to service B and communicate. In the concept of a service mesh, it does not. Deployed with each service is this sidecar proxy. Now the sidecar proxy will kind of do the routing for the proxy. It's, a proxy. So service A communicates with the proxy running inside of its same pod. So it communicates with the proxy inside this network boundary. The proxy will then reach out to the service mesh control plane and say, hey, am I allowed to talk to service B? The control plane can reply and say, yes, you are allowed to talk to service B, and here's the address to service B. It will create a mutual TLS connection off to service B, but it doesn't communicate directly with service B. Rather, it communicates with service B's proxy as well. Now this is running inside the same pod as service B's container. So then the proxy reaches out to the control plane and says, hey, is service A allowed to connect to me? Oh, yes, it is. OK. And so then it routes the traffic off to service B. The reply comes back, it goes through the proxy, it goes through the other proxy, and it goes back to service A. Now we have some interesting concepts here that is really, really cool. There's mutual TLS between both of these services, but the source code of the services didn't need to change to empower that. That's really powerful. By putting a proxy into each service, we can empower a whole lot of functionality that we didn't have before. Let's dig into some of that functionality. Observe, control, and secure. At its most basic level, we do that, observe, control, and secure. We can observe the traffic. As service A communicates with service B, we can notice that that happened. We can grab logs. We can start to talk about service health and metrics. Secure, we have that mutual TLS between the two services. Outside of a pod security boundary, there is no unsecure communication at all. And in control, we can start creating access policies to say, service A can talk to service B, but service Z can't talk to service B. Taking that to the next level, we can do some interesting things where we can talk about additional functionality. Since we're watching all of the traffic in our cluster, we can do things like track service health. Hey, I noticed that service A was reaching out to service B, but service B gave it a 500. Maybe service B is having trouble. We can grab logs off of all the services. Here's the uptime associated with service B. Here's how often it usually replies. Here's the health checks associated with that. We can kind of get a feel for how these services typically behave. And then what's really cool, because we're watching all of the traffic in our cluster, we can map out how the cluster communicates. Now this isn't what the developer thought would happen between the microservices. This is the actual traffic flowing between the microservices. Now what's interesting is we might be able to compare this with what the developer thought would happen and say, I think you might have missed something. Are you really reaching out to the config service, or are you using the hard-coded value you used in debug? That's kind of interesting things to know. Taking a step further, we can look at other things. Because we're routing all of the traffic, we can start to make intelligent rules around this. Maybe we would like to do an A/B test, where we can send a portion of the traffic to version 1 and another portion of the traffic to version 2, and kind of see how those two are behaving. See which one has more customer engagement, which service is able to perform better, or identify the service that is more tuned to the task at hand, and then start routing all of the traffic towards that successful piece. Or perhaps we want to have a beta channel to give new users access to the code faster, or a canary channel where we can validate that the system behaves as we expect. And then what's really cool, circuit breakers. One of the things that we are really good at doing is retrying. And built into a service mesh, we can do automatic retries. But if we retry, if service B is, trying to crank through a big piece of workload, and ultimately it's not able to make it through, the first thing everybody else is going to do is retry it. So as service B starts limping along and coming back up, we're just going to DDoS it again and kill it again. Instead, what we can do in the circuit breaker is we can notice that that service is not behaving very well, and we can fail the request at the service mesh. Traffic will never get to this failing service for a period of time. Now, unlike traditional circuit breakers, you don't have to go walk outside and flip the switch anymore. Instead, we can wait a little bit. Hey, let's try it in a few seconds or in a few minutes and see if the service is behaving better. Once the service is healthy again, we'll close the circuit breaker, and now all of the content can flow as it normally did. Circuit breakers are a really powerful way to heal services dynamically without having to do any manual intervention of the services. Any questions so far? Yep. Good question. How much overhead is that? Ask me in about 10 slides, because we'll talk exactly about the overhead. Good call. Yep. So Kubernetes would have the concept of a service. Is it analogous to these proxies, or are they independent? Good call. So how does Kubernetes service kind of sync with a service proxies service? To do that, let's dig into Istio and Linkerd and talk exactly about that. Oh, and I realized I missed one thing on the way. Here's a dashboard that kind of gives us both service health and network topology, and this is possible because we're routing all of the traffic between things. So we want to look at Istio and Linkerd. Oh, so one of the wonderful things about a service mesh, if a microservice is to own its own data store, it's really easy to forget and actually call the other guy's data store. With a service mesh, we can isolate a database so that only that service can talk to that database and avoid this kind of cross-join of traffic. So let's talk about Linkerd and Istio. Now, we could get into a bake-off of who has more features or who is faster, and that's interesting, but less relevant because, of course, everybody's going to catch up with the latest feature, and so kind of comparing features is less of a win here. Instead, I'd like to start with a methodology of how things work. Linkerd really focuses on writing their own components, running their own stack, which is really cool. They've contributed a lot to both the Go and Rust communities. But they really want to build everything in-house. Their goal is to have a very simple install experience and a very fundamental set of features that does really interesting things. The downside is if you want more, you need to pull in external plugins to facilitate Linkerd's accomplishing those tasks. It has that same mechanism where it has a control plane, it has a proxy sidecar, a sidecar proxy within each container, and that's how it's able to route the traffic. By comparison, Istio has all of the things included out of the box by default. You can choose to turn things on and off, and we definitely do, but all of the things are there. Istio focuses on including community packages, the best of the industry, and so you'll see a lot more brand names as you install Istio as compared to Linkerd. Ultimately, Istio does that exact same thing, where they have that control plane, they have a sidecar proxy with each container, and it will route traffic between the services or into or out of the cluster through these sidecar proxies. Both of them you will use custom resource definitions, CRDs, to create their content. Istio now has an operator, which is really interesting. And as you install Linkerd, you can see all of the CRDs. It's really fun to watch them go past. You asked about how do these compare. Here's a definition of a virtual service. Now this in Istio would replace a regular service and starts talking about how to route traffic between things. Now I'll create in Istio destinations, service points, and I'll create this service that will route traffic between those endpoints. So, demoing service mesh. This is really cool. I'm going to have so much fun with this. I have here two clusters. One is an Istio demo cluster, one is a Linkerd demo cluster. And so we can kind of poke at them without interfering with each other. Let me switch off to the Linkerd cluster. Now Linkerd is known for being really easy to install, really easy to set up. I've already downloaded the Linkerd executable and put it in my path. And so from here, I'm just going to start installing Linkerd. I went off to the Linkerd Getting Started page, and it walks us through the process of doing it in a really, really elegant way. That Linkerd Getting Started doc is gorgeous. So I'm going to start off by saying Linkerd check -pre, well, --pre, and it'll kind of take a look at my cluster and say, how are you doing? Do you have all the pieces in place that I need to use to be able to accomplish this task? And ultimately, yep, it says my cluster's good to go. Awesome. Next step, let's go install Linkerd. I love this in the demo last hour. Linkerd install. Here's all the CRDs that we're about to put into Kubernetes. Here's all the pieces of Linkerd that get us started. And so Linkerd install is really cool at getting a feel for that. Once the cluster administrator says that's OK, then I'm going to, Linkerd install, pipe it to kubectl apply -f-, and now we've got all of our pieces flowing into our cluster. Now that we've got all the pieces in place, kubectl get namespaces, we see we have this additional Linkerd namespace, which is perfect. Kubectl get pods inside the namespace Linkerd, and we'll see those starting to spin up. I love this tool that comes with Linkerd. I can say Linkerd check. Last time I did the --pre, which just took a look at the cluster but didn't examine any of Linkerd's content. But this one will actually go through and look at all of the Linkerd content within my cluster and tell me if it's running. I got all green checks, so I know that Linkerd is working just fine. That is great. Kubectl get all --namespace Linkerd. And I've got all of the content ready to go. All these services are running as cluster IP, which is perfect, as I expect. That means they're not publicly exposed. So I will run Linkerd dashboard, and that will proxy me into the cluster and pop up Linkerd's dashboard. I'm going to switch off to the Linkerd namespace and take a look at deployments. And we see that already all of the content is being watched. Linkerd actually watches itself, putting proxies, sidecars in front of its own content, which I just think is really elegant. Well done. For each of these, I can pull in the Grafana dashboard just by clicking on the Grafana logo. And here is the metrics associated with the content for that service inside Linkerd. Now this Grafana dashboard was pre-installed, but I could definitely take the Linkerd Prometheus sync and push that off into a more durable Linkerd Prometheus store and start to create more dashboards around that. So Linkerd will definitely dump that content straight into Prometheus so I can make better actions there. So in a nutshell, that is Linkerd, and we could dig into more of the content of it. But let's switch over to Istio. Any questions on Linkerd before I do? Ooh, now my Linkerd dashboard is really mad. I would definitely recommend the talk, going to the talk that happened last hour, because it was a great deep dive into Linkerd. If you have the chance to see that talk, that was really cool. Now, it might be interesting to pull up those stats from the dashboard, but I'm going to say Linkerd stat deploy, and I'm going to pull up the statistics that I saw in the dashboard, but here I'm doing it from the command line. So if you're more comfortable with the command line and getting the stats that way, this is a really, really powerful interface. Okay, let's switch over to Istio. Okay, switching kubectl over to Istio and switching Docker over to Istio. Now we've got our Istio cluster ready to go. Now I've done the install of Istio already. Kubectl get all -- what is it? Get namespaces. Kubectl get all namespace Istio system. So similarly to Linkerd, it created its control plane and its own namespace, and it has all of the Istio content in place. Now, as you install Istio, similar type of mechanism, the Getting Started page is really elegant at getting you from just started to getting all the things downloaded to putting everything in place. Similarly, I already grabbed the Istio command line interface, and so that's ready to go. One of the things that you'll do as you install is pick a profile. And in this profile, these are kind of the default settings, the default things that are turned on and turned off. I've chose demo mode in this case, which gives me these features. But you could also choose a minimal install that actually disables mutual TLS if you chose to do that. Just get the logging and the monitoring, but not the security. That's totally fine. As I install it, like I did with Linkerd, I will turn on, not that one, I will turn on the namespace. So I'll come in here and I will label my namespace. In this case, I will label default. And say injection is enabled. Once I have that turned on, either in Linkerd or in Istio, all of the content that I provision from then on will have that sidecar proxy automatically injected. Okay, so Istio has this great application that makes demoing this really, really cool. Now we're talking about north-south traffic, but this graph goes from left to right, so there is that. But then we start talking about east-west traffic, and it's also still going left to right, so there is that. But we start out with our traffic coming in to the ingress, and we'll put a proxy inside this ingress controller, much like we would put a proxy anywhere else. So as soon as the traffic comes in, now we'll do mutual TLS between all the other services. So here's another sidecar proxy inside this product page. It happens to be a Python app. The product page will reach out to product details and hit that sidecar proxy, grabbing the details there. The product page will also reach out to a reviews service. This is one of 3 Java apps. And the reviews service in version 1 shows no stars. In version 2, it shows black stars. And in version 3, it shows red stars. And so we'll use these 3 different versions of this microservice to see how we would kind of do a rolling update, or how we could shape that traffic in really interesting ways. In version 2 and version 3, to know how many stars it needs to get, it will reach out to the rating service. All of these brown boxes are the sidecar proxies. So we have north-south traffic coming into the ingress proxy. We have east-west traffic going between all of our containers. And so outside of each pod boundary, there is no traffic that is not secured with mutual TLS. Okay, so let's fire up this app. Now I go here, and right now we see that there are no stars under the reviewer. We're using version 1. Now to accomplish this, we installed this. Monitor resolution is fun. We installed this virtual service. Now this virtual service very specifically says, please route all traffic to version 1 of this service. Now ideally we wouldn't have all 3 of them running at the same time, but I do have all 3 of them running just so that we can see the content go by. So we want to try out version 2 of this service, but let's only send a little bit of the traffic just to kind of get a feel for how this is going to work. So we'll still send 90% of the traffic to version 1, and we will send 10% of the traffic to version 2. (90-10). This is actually not 90-10, this is 80-20. That's cool. So we're going to send 20% of the traffic to version 2 and 80% of the traffic to version 1. So now as I refresh this page, we'll see that 4 times I will get no stars, and 1 time I will get black stars. Unless I'm really unlucky, and then I will never get black stars. There we go, there's black stars. So now we can get a feel for, is our service behaving? Is it doing what we want? Is the star data accurate? And once we've got that kind of solved, then we can upgrade and we can say, okay, I would like to go completely to version 2. So now we're not going to route any traffic to version 1, only to version 2. Let's apply that configuration. No downtime. And now I will always see the black stars. I put this virtual service in place of a regular Kubernetes service to get that additional routing configuration. Okay, so now we want to talk about upgrading to version 3. And I have a beta tester, his name is Jason, and the tester is going to go validate that version 3 works correctly. So I'm going to route all the things where we have a user named Jason to version 2 and everyone else to version 3, which in hindsight I think might be a little backwards. Let's send most people to version 3 and Jason to version 2. Okay. That's not right. Reviews Jason v2 v3. Reviews Jason. Fail. Nope, I'm going to crash out of that demo. Okay, so Jason was able to do that. The interesting thing, though, is if I sign in as Jason here, I'll get the other one, and if I don't, then I'll get the regular one. I think that's really cool. So crash out of that demo. So now we want to send about 50% of the traffic to version 3 and 50% of the traffic to version 2. So let's apply that rule. And now when I push the button, I'll get black ones and I'll get red ones, and that happens about half the time. Now it is random, so I may get black ones a bunch of times in a row. And once I've proven that that works, now let's flip completely over to version 3. And now we're all the way on the red ones. So we saw some interesting things. We could route traffic between 2 services. We could route it based on rules of headers or logins or other details. We could create a beta channel where users that have a certain header set or a part of an auth group go to the new version. And all of this is possible because we're standing in between those 2 services. Any questions on Istio? Yep. How does it map to a user? Good question. How does it map to the user? When I'm in here, book info, networking, let's go open up that one again. In this case, it's matching a header, and so it's pulling that data out of that header, but I could match it on other information. So this one, oh, that's exactly the same. It also matches on header details. Is the application looking at the header? Oh, is the application setting the header? Yes. So once I log in, I've got that cookie set, not that cookie. Yeah, I have that cookie set, and as I hit this product page and it makes the request off to the reviews page, it's setting the proper headers so that the review service can understand which user is hitting that service. That was a great question, thank you. What other questions do you have right here? Yep. Am I familiar with OpenShift? A bit. Mm-hmm.
You know, let me get you the mic. It sounds like it's getting complicated.
So now your mic.
Okay, so with OpenShift, you have the ability to do the rolling deployments that we just displayed there. How does Istio extend that, or why would you want Istio? Sorry, I have no idea.
Interesting. So why would I want Istio if OpenShift already kind of has this rolling deployment piece? Built into Kubernetes, we also have a rolling deployment where we can spin up new pods and start pushing traffic to it and then shut down the old pods. The difference is that I have portions of the traffic going to each one. So it isn't like, okay, we're done with version 1, everyone go to version 2, but rather I can have both of them happening at the same time, and I can grab a sliver of traffic and move it over at a time. And at the point where the new one is behaving, I'll move faster, and at the point where the new one isn't behaving, I'll move it back. I haven't terminated the old pods. I haven't made the choice to move all traffic to the new pods. Both of them are running at the same time.
Yep. Actually, OpenShift can also do that, but it's because it's using Istio under the hood.
Ah, so yeah, I'm comparing Istio to itself. That's awesome.
Yeah.
I learned something cool. It's kind of like, as long as you want to use Knative, you're already using Istio?
Yes.
Yeah, that was a great question. Thank you for clarifying, too. What other questions do you have right here? The next person has to ask the question from the back corner so that he can run. No, I'm just kidding.
Do you have a demo ready for Linkerd?
Do I have a demo ready for Linkerd? A demo application? I don't. But part of what makes Linkerd so powerful is that initial startup experience, and so that's really the Linkerd demo that I wanted to highlight. Okay, so while we're here looking at Istio, let's look at some dashboards. kubectl get svc -- namespace Istio system. Now there's a few, but I flipped one of them over to be, oh, I didn't, haha. Okay. Error upgrading connection. This may be a very short demo of demoing all the dashboards. Yes, we will totally fail to run all the dashboards, because these dashboards are totally awesome. Oh, here we go. So we have a Jaeger dashboard. If I look at this Jaeger diagram, this is how the traffic is actually flowing through my cluster. We start off coming into the product page, and then the product page will reach out to the Istio mixer. The product page will also reach out to the details, and the product page will reach out to the reviews. The reviews will reach out to the ratings. This is an actual dashboard of what's happening inside of my cluster. Not what the developer thought was happening, but what's actually happening, which is really cool. I'm going to break out of that. Let's look at the next dashboard. We missed the Grafana dashboards in Istio. Ooh, we're going to miss SCaLE too. Bummer. The pod does not exist. Bummer, because it says that all of them are ready, but the dashboards don't. The cool part is that we get to see there is a Prometheus sync inside of Istio, and so we're able to see really great Grafana dashboards. There's also SCaLE, which gives us kind of a great architecture around the things. Jaeger allows us to put in trace IDs and to be able to see a single request as it flows between all the services. And so all of these dashboards really work together in concert. The bummer part is you have to know where each dashboard is, because they're all kind of separate packages that Istio happens to install together. By comparison, Linkerd has a single dashboard that kind of puts them all in one place, meeting that similar methodology of Istio grabbing all of the industry standard components and bundling them together, and Linkerd focusing on building first-class components and really simple experiences. So there's kind of a difference in methodology there. So we got to see some really interesting things both in Linkerd and in Istio. And I like to make this analogy similar to crawl, walk, run. At the first level, at the crawl stage, a service mesh allows us to see the traffic in our cluster. So we'll get monitoring, we'll get logging, we'll get service health. I know what services are up, I know what services are down, I know how each service is performing, I'll get logs and metrics around that. As we get into the walk phase, here's kind of that step above that, where because I'm watching all the traffic, I can do really interesting intelligent routing, A/B testing between things, or rolling deployments where I don't push all of the traffic across. And then as we get to run, we can look at that traffic pattern and make intelligent decisions. We can build policies around it to say, hey, I just noticed a new dashboard is trying to connect to this database. Do I want to allow that? Or is this a rogue container that I should block? And we can make those intelligent decisions. We can have circuit breakers that turn things off, or we can spin up additional containers based on the analytics that we're getting out of our dashboard. The quote that I love from Zach Butcher, he wrote an Istio book, which is really amazing. He says, if it doesn't have a control plane, it ain't a service mesh. And so that's kind of that defining characteristic. We put a proxy sidecar on each container, and we have a control plane that allows us to communicate, to make intelligent decisions around our things. So you asked a question about what is the impact around this. Well, as we look at this, on the left is all the things that we had before. We have our Kubernetes control plane, we have our worker nodes, we have all of our pods, we have cAdvisor, we have kube proxy. That's all the things that we had in Kubernetes before. And what we added is all the things on the right. We have all of our service proxies, we have the control plane. The control plane is made up of multiple pieces, all of the sidecar proxies. So basically what we did here is we doubled the number of containers running in our cluster. Now the Envoy proxies are probably a little bit lighter weight than the Tomcat apps running inside the containers, but we're also doing a lot of TLS communication, and so maybe we're even doubling the amount of compute that we're doing in our cluster. This is a non-trivial impact if our only goal is to get that, yep, I checked the security box. You may not need a service mesh If what you're trying to optimize is less spend, just grabbing the stuff on the left is completely sufficient. But if you're after those features of controlling, securing, and observing, controlling, and securing the pieces of your cluster, then it's worth taking that additional barrier, that additional burden of this additional compute to empower those features. Observe, control, secure. Because we're able to see all of the traffic moving through our cluster, we can make really intelligent choices. Transparency of communication. We can see all of the traffic flowing there. We can log it. We can monitor it. Control. We can take additional steps. We can trip circuit breakers if a service is behaving incorrectly, or we could route between two different versions of a service. And secure. We have mutual TLS between all of the things. If these are features that you really need, a service mesh can definitely be helpful. And here's kind of my checklist. You might need a service mesh if you're running highly sensitive workloads, like PCI or PKI, if you have HIPAA things, if you must have security in all the things, both in north-south traffic and in east-west traffic, then a service mesh is perfect. Alternatively, if you're running untrusted workloads, such as multi-tenant workloads, then a service mesh can help you isolate the traffic between each other. An API gateway, by comparison, will only validate that the traffic coming into your cluster is okay. But once one tenant launches a poisoned pod, then it can reach out across namespace boundaries to all kinds of things without a service mesh. A service mesh is great for multi-tenant deployments to keep everyone in their lane. A service mesh is great when you need security in depth because you can't communicate between containers until the control plane approves it. If you need to do A/B routing or a beta channel or these more controlled rollouts, then that's a great use case for a service mesh. If you have one of these use cases, a service mesh like Istio or Linkerd can be a great choice. If you're only running first-party workloads and you only have a few services and you trust all of them, then you probably don't need a service mesh. And avoiding that additional compute cost can be really, really helpful. Any questions?
I actually have one.
Yeah.
So there's a fair amount of overhead associated with the service mesh in terms of extra sidecar containers and needing to manage the service mesh and everything else. How can you tell when you're at the tipping point of actually needing one? Because you have that list of items that a service mesh is good for, right? But if you only need one of those things, some of the time it's probably not worth installing one.
Agreed.
Any recommendations on how to tell when you're at the tipping point of when you really do need one?
Good question. When do I know that I'm at that tipping point of when I need it? I tend to refer back to this list. Am I running multi-tenant workloads or very secure workloads? That's usually the spot where I need it. If I'm trying to get really in-depth metrics around my containers, there's often better ways to get that than a service mesh. And so I'll probably not reach for a service mesh just to get metrics. But if I need those rolling updates or I want to run Knative, then running Istio can be really helpful. It is a fuzzy boundary, though, and so ultimately have that conversation with your organization and decide together that it's time to dive in.
Has anyone tried to do service mesh with more traditional tools rather than rewriting proxy, rewriting the sidecar things? No, I mean, we know for a long time how to do proxy and how to do canary or A/B testing using plenty of old school tools that work quite nicely in the containers and in Kubernetes. Is there not an actor, another, I don't know, kind of solution saying, well, yeah, you can just use Nginx and this and that and plug it to Prometheus the same way and do reverse proxy the same way and do TLS the same way?
There's a couple of different ways to do that, and that's really elegant. You know, how could I do this without sidecar proxies? The first way is, I just don't. Yeah. Next up, I could implement all of these things as code in my application. And at that point, then I need to implement it in each service. So, you know, if I have a Java service, then I need to pull in the proxy code, and I need to remember to configure it. So in time, we kind of reach for the third way, which is I'm going to abstract that into a library. But now each microservice needs to remember to pull in that library. I'm still doing it all in the code. Part of the beauty of this fourth step of having it outside of the code is it's removed from the code. I can get Kubernetes to enforce the sidecar proxies in each piece. I don't need to build in retries or circuit breakers into all my code. I can leave that as an implementation detail for my cluster, for my service mesh, and my microservice can just focus on doing the task at hand. So there definitely are other options, but they're generally more developer intensive. That was a great question. Thank you.
If one were to decide to install Istio and Linkerd and go down that road, and the customer says that's too much workload, is there kind of an undo switch, like you undo that, or is this a one-way street?
Good call. So if I want to install Linkerd and Istio, am I now fully committed, or is there a backout mechanism? What's really cool is that we saw a little bit in Istio of routing traffic between two services where both of them kind of had the same name. But outside of that use case, pretty much I'm just connecting to that service by name. I just happen to have a service mesh proxying that traffic. So provided that I'm routing between services in the normal way, I just uninstall my service mesh, and I'm back to vanilla Kubernetes and doing all the things. One point of clarification, though, I probably don't want to install Istio and Linkerd. I probably want to pick one. Ultimately, you know, which one to choose, that'll be an interesting question, and we can argue about that one over beers.
With the initial uninstall, or the uninstall of Istio or Linkerd or whatever, would you have to redeploy all your pods because now they all have the sidecar?
Good call.
Or don't have the sidecar?
Yeah, if I was to uninstall my service mesh, all of the sidecars are still in the pods that were launched before then. So yes, I would need to then kick off my deployments to redeploy everything. I can do that in the normal, you know, rolling update way. I can just kind of walk through my pods, killing them off, and let my deployments recreate them. And because I don't have that piece inside Kubernetes that will automatically inject the sidecar, then the new ones just won't have the sidecar. In the meantime, what's really interesting, I've done this. Once you kill off the control plane, they're trying to check in to say, can I connect? And there is no control plane to approve it. So pretty much your cluster shuts down. So in general, I recommend doing that offline, where you have a little bit more control over, you know, taking down all the things without impacting customers. A gentler way to do that is we saw as we turned on that Istio namespace, we just told it to inject the sidecar proxies by labeling that namespace. We can unlabel the namespace and then tell all the deployments to kick off. Now they won't have the sidecar proxy. Now we can uninstall Linkerd, and then we won't get that same, you know, locked up, can't connect process. That's also a good way to test, you know, what if we didn't do this? Just turn off the namespace and redeploy everything and see if things speed up or slow down.
So do you and then you.
Oh, thank you. Is it possible to add services outside of Kubernetes to the service mesh?
Good question. Can I add services outside of Kubernetes to the service mesh? One of the things that do I have it? No, I don't. It's right here. Not here. One of the things that's really helpful in this diagram is we have that ingress proxy. We have that ingress controller that has a proxy. Similarly, we can have an egress proxy that is allowed to monitor the traffic leaving the cluster. And I may choose to have one egress proxy for all outside traffic, or I may choose to have like a shadow service, an egress proxy for each external API. And that can validate traffic as it leaves the cluster. Now on the upside, I can capture all the traffic that have the sidecar proxies enabled. But if I choose to disable a particular namespace, then yeah, that traffic is unrestricted, and it can flow out of the cluster unimpeded. So it's not a boundary, it's not a firewall, but it is a validation rule for all those things that the service mesh controls.
Is this stuff compatible with stateful sets?
Does Istio use stateful sets?
Oh, no, so let's say I have a stateful set. Is it compatible with all the pods that a stateful set would stand up?
Good question. Is it compatible with all the pods in a stateful set? I honestly don't know. Do you know? Yeah. The answer is yes.
Oh, right, yeah.
So yes, it's compatible that you can get the MTLS, but you have to do your own service discovery if your stateful sets are individually addressable. Like if you have, you know, say Postgres, you have a master and a slave, you're going to have to handle the discovery so it knows which is master and which is slave.
Oh, good call. That totally makes sense.
Also, last I checked, Istio still doesn't do persistent TCP connections, which, I mean, a lot of the reasons you use stateful sets are databases, and transactional databases tend to want a persistent connection from the client, which last time I looked at this did not work with Istio. It was something you could actually do with old Linkerd. I don't know whether or not you can do it with new Linkerd. Yeah, okay.
Yeah, persistent connections. In theory, you're only securing the connection, and then once the connection exists, you just don't hang up. But yeah, I could see how timeouts could really break that. Good call.
All right, you know, let me, so everybody.
Interesting. So Linkerd does automatic traffic detection, so it won't proxy. Yep.
So Linkerd will do automatic protocol detection. So for something like Postgres, it will recognize that that's not a protocol that it supports and will not proxy that traffic until we do support for MTLS for TCP.
That sounds perfect. Yeah. Once we've got TLS, mutual TLS for TCP, then we can do all kinds of magic things. I like that.
I got into this because when service meshes first came on the scene, I immediately had like database uses for them and was very disappointed to find out that I couldn't actually do any of those.
Right. Well, this has been a lot of fun. Thanks for letting me play.
Okay. We do have one more session in this room. At 4:30, Karen will be comparing AKS, EKS, and GKE so that you know which cloud provider to choose for your hosted Kubernetes.
Ooh, that sounds like a really good session. I'm not sure. Which one should I choose?
So for our last talk of the day, Karen is going to explain to us the difference between the major cloud hosting platforms for Kubernetes. Tell me, give you a chance to get ready. This has been the containers track at SCaLE, our 4th run at the containers track. We've had a highly variable schedule, but we are closing it out with an excellent talk. We will be back at SCaLE next year. The call for papers goes out in October, and submit a talk. So, Karen is going to explain to us the difference between cloud platforms for hosted Kubernetes. So welcome, Karen.
Thank you. Is the microphone picking up this time?
No.
No.
Bend it towards your mouth.
Okay. Just a little bit. Okay. We had this problem last time. Is that good? Good? Better?
Say a little bit more.
Saying a little bit more?
Yeah.
Yeah.
That seems good.
Okay.
Okay.
Okay. My name is Karen Werner. I'm the tech evangelist at StackRox. We do security software for Kubernetes clusters. This talk is called Evaluating the Top 3 Kubernetes Providers. That's not actually my title. I forgot to update the slide. These are the top 3 hosted cloud versions. So first off, I've given you my name. I was an SRE DevOps engineer for a long time. I'm a totally sane cat lady. And I have a Twitter handle, which I've had for a month after avoiding Twitter for a very, very long time. Okay. So we're going to talk about Amazon's Elastic Kubernetes Service versus Azure's Kubernetes Service versus Google Kubernetes Engine. So first off, we'll start with version support matrix. This one is I find this very interesting in kind of sad ways. So vanilla open source GitHub Kubernetes master, they just released version 1.18 to beta. It should be full release by the end of the month. We're kind of all over the place. All 3 providers have 1.14 as a default, but oddly enough, GK was the last to make 1.14 their default version for new clusters. And they only did that a couple weeks ago.
This is current as of this week?
Yeah.
Okay, that's scary.
Yeah. Exactly. Yeah, I mean, yeah, you'd figure that Google, it's Kubernetes, it's Google, they're kind of behind. It's interesting that Azure, and this hasn't always been the case, but it's interesting also that Azure is actually the most up to date with the latest versions. They're still in preview and unsupported, but they're still up there. And the slightly scary thing is that Amazon is still at 1.14, and they released 1.14 for their platform in September, so it's been almost a full 6 months. And Kubernetes itself has a 3-month release cadence. They put out a new release every 3 months. So where's 1.15? Amazon? I don't know. They also don't do preview releases, so you can't even see if something's coming around the bend. We have no idea. They've been completely silent. So probably the first thing you're going to ask about a hosted managed Kubernetes, well, what's it like to do upgrades and maintenance? How much work am I actually going to have to do? Control plane upgrades. So this is what, the basic thing you'd think they manage. These are what correlate to the master nodes if you were running your own cluster. This is where the API, Kube API server sits. For your cluster, this is where the scheduler runs. This is where a lot of the critical admission and cloud controllers will run. EKS, all of this is manual. You have to initiate the control plane upgrade. AWS will actually upgrade the control plane, but all those add-ons, and by add-ons I'm talking even the container network interface, which runs on the nodes, which you're required to have, core DNS, which you have distributed in cluster. The user has to manually upgrade all of these add-ons. You can automate it, but you're still responsible for the upgrade. AKS, user kicks off the control plane, but Azure will take care of everything. And in GK, this is automatic. You can schedule these upgrades for a maintenance window, and because they should be 0 downtime, it should just automatically happen and you don't have to worry about it. Node upgrades is similar. EKS, the user initiates. They have when EKS launched, the node groups were kind of strange. You created an auto-scaling pool with certain requirements, and it just had to be able to run kubelet and be able to join the master of the cluster. But at reInvent in December, they introduced managed node groups, which are slightly more managed, but not significantly. They will. It does ease the creation of the node group, and once you initiate the node group upgrade, it will drain and replace your nodes. But the trade-off is you lose a lot of configurability, a great deal of configurability. AKS user initiates. AKS will take care of all the upgrades for the nodes. And GKE, again, it is automatic. You just schedule a maintenance window, and it will upgrade your node pool for you. Node health monitoring. Amazon, Azure, neither of them have any node health monitoring. They'll monitor your VMs, but they're not aware of the kubelet or whether or not the kubelet is healthy, whether or not it's talking to the master successfully. Whereas GKE has automatic node repair. It will both detect issues and either repair them or replace the node. All automatic, all for you. That's on by default. So looking at the nodes, this is a grid of supported operating systems and images. EKS defaults to their Amazon Linux. You can also choose Ubuntu or even a custom AMI, and they have full Windows support, which is interesting because Kubernetes itself, it's still beta. If you're using a managed node group, which I mentioned before, you can only do Amazon Linux. Again, this is one of those examples where you lose configurability if you use the managed node group. You can still create a self-managed node group with any image you want, as long as, again, it can join the cluster. AKS, the only Linux version they support is Ubuntu, and they also have Windows Server in preview. GKE, they default to the container optimized operating system, but you can also choose Ubuntu, and they also have Windows support in beta. In Kubernetes, for vanilla Kubernetes, any compatible Linux, and again, Windows is in beta. Container runtimes, EKS uses Docker, AKS uses Docker Moby. I am like many people, I still don't understand exactly what the difference is, but AKS docs say Moby, so Moby. GK uses Docker by default, but you can also opt to use Containerd for your container runtime. And vanilla Kubernetes supports Docker or any runtime which conforms to their container runtime interface. Technically, Docker does not conform to their container runtime interface. It actually uses Containerd as a shim. So even if you think you're not running Containerd, if you're running Docker, you're also running Containerd. All three have GPU support. You can install the NVIDIA device driver, and if you're on a system with GPUs. And all three support node pool auto-scaling. However, in EKS, again, you have to install the add-on and manage it yourself. This has really important security implications. The autoscaler, since it's creating VMs, you know, in EC2 it's creating instances, in Google and Azure it's creating VMs, it has to have cloud provider API permissions and credentials. So normally you would install this on the control plane where it's away from user workloads, where it's protected. But because you're required in Amazon to install it on your user nodes next to your user workloads, it's much more difficult to protect those credentials, especially even if you're very protective of the credentials. If any other workload on that node gets compromised and it compromises the node, you're out of luck. For the control plane, so EKS by default is highly available. You can't off-floor, and they will deploy to 3 availability zones in your region. AKS, the documentation does not say. It is strangely silent on this point, because you think if it were, you know, in most cases if you're looking at something, they're super happy to say, hey, you know, super highly available, we've got redundancy. They don't say anything, and there's also, I did some digging, I'm trying to, did I miss something? Googling, I found this one bug in one of their GitHub repos where it was not specifically about this, it was about the high availability of a related component. But since they had a Microsoft dev on there who was answering questions, somebody said, what about the control plane? Is that redundant? And in a list of 3 questions, and the dev answered every other question, and yeah. So I can't say for certain, but I would infer that it is not a highly available control plane. GK, you can either deploy a zonal cluster, which is just in one availability zone, or a regional. So zonal clusters, one availability zone, obviously not highly available. Regional, yes, it's highly available. There's a weird thing about regional clusters, though. It doesn't just make the control plane regional. If I create a node pool for that cluster, it's actually going to, and I say I want 3 nodes, it's actually going to put 3 nodes in each of the zones. So you end up with 9 nodes. So if you want a cluster with 3 nodes, then just tell it you want 1 node, and you'll end up with 3 nodes. So right now, I didn't put it in here, but there's a pricing. Currently, Amazon is the only one of these 3 providers that charges for the control plane, and it's 10 cents an hour. They just knocked it down from 20 cents, I think, last month. AKS doesn't charge anything. Google right now doesn't charge anything. They just announced that starting in June, they will start charging 10 cents for the control plane. 2 years ago, they actually did charge for the control plane, and they had different prices for zonal and regional, but it sounds like it's just going to be a flat 10% or 10 cents an hour. But right now, EKS is also the only one, even though they have these service level agreements, EKS is the only one that financially backs its SLA. But GK says once they start charging again, they will also financially back their SLA. Oh, and pricing, well, just mentioning pricing. Other than the control plane, everything else, you're generally just using their, whatever, it's EC2 or their compute engine, or for AKS, their VM, their VMs. For the rest of your cluster, it's just the standard price for whatever virtual machines you're using, whatever storage you're using, whatever else. And the control plane, 10 cents an hour, I forget what it comes out to a month. So if you're running large clusters, it's going to be an insignificant part of your overall bill. However, it mostly impacts very small houses or hobbyists. The control plane is not even part of the Amazon free tier, but Google is going to allow you 1 free zonal cluster per project once they start charging. So networking options. For Amazon, you're required to use their AWS VPC CNI. And this puts so what this does, they have, in EC2, you have elastic network interfaces. So these are the virtual network devices which attach to your instances and provide you network access. Well, they're putting the pods directly on the VPC network along with the nodes, by using elastic network interfaces. So this has some strange side effects. For one thing, they default to putting your pods on the same. So security groups, EC2 security groups apply at the ENI level. Even if you have multiple addresses, the elastic network interface, they all get the same security group membership. By default, the AWS VPC container network interface puts pods on the same interface as the node. So you cannot give different security group rules to your pods and nodes. This is bad. It's, your pods should not be able to directly address. You should be able to firewall and give them different rules. There is an option to customize the behavior, but it doesn't work with managed node groups, because you can't customize the image or its installation. So you have to use self-managed node groups. And it's not an insignificant amount of work either. It's actually a fair amount of upkeep. And you're also limited. Different EC2 instance types can support different numbers of interfaces and different counts of IP addresses per interface. So it's completely, you have to do some math. It's completely, how many pods you can put on a node depends on the size of the node, on the node type. AKS lets you choose between KubeNet, which is the default network plugin for Kubernetes, and it does some magic routing on the back to make it VXLAN compatible. Or you can choose their Azure CNI. The Azure CNI is very similar to the AWS VPC CNI. It puts the pods directly on the same VPC network as the nodes. And so therefore, it also makes it more difficult to segregate your pod and your node traffic and the firewall rules that apply to them. GKE, QNet, they do magic. They are going to soon, right now it's an option, but they will start making their IP aliasing the default, which also puts the pods on the same VPC network. But in this case, it's probably, I'm not sure how they're going to manage, how they manage the firewall rules, but overall it's a bit more secure because this way they can prevent spoofing, they can do actual end-to-end checks. I talked about this. Okay, network policy support. Once again, EKS, you can use Calico, but you do have to install it manually and manage upgrades. For Azure, either of the two network choices support Calico. The Azure CNI also supports Azure policy. These are both implementations of the network policy API, so you can actually use the same manifest for either one. They behave the same. Calico is a nice addition, though. They have their own additional resources. Network policies apply at the namespace, so if you want to do some blanket network rules, let's say you want to block access to the kubelet port from all namespaces, you have to put a network policy in every single namespace, which is upkeep if you have a very dynamic cluster. Calico has a global network policy which can apply to your whole cluster. So if you have those rules that you want to apply to every namespace, that makes it a lot easier to manage. And GKE uses Calico, and you can enable network policy at any time. Azure, there's one thing about it also, and this is not the only case where this happens. If you do want network policy, you have to create the cluster. And Azure does this for a lot of features. And they add, even as they add new features, some of them come up this way. So if you do use Azure, I suggest you just automate or have a process where when they release a new feature you want, you have a nice way just to move your workload, create a new cluster, move your workload over, and be happy. So standard Kubernetes security options. RBAC is the default for everything. It is always enabled on Elastic Kubernetes service. This is another one of those places where Azure you have to select RBAC when you create your cluster. Pod security policy is also always enabled in AWS, optional in the other three. Pod security policies are almost certainly going to be deprecated soon, but there's no standard replacement yet. So if you're using them, keep using them. If you're not using them, don't invest a huge amount of automation in it. They are nice to have to enforce best practices, but there are other ways to do it that are probably better investments. The Kubernetes API endpoint, by default, all three providers leave it open to the internet. This is bad. There's usually no reason that the entire internet needs to see your API endpoint, but more importantly, there have been some very important vulnerabilities, CVEs discovered against the endpoint, including late last year we saw the billion laughs attack, which allowed unauthenticated users to perform basically a denial of service attack against your API endpoint. So you really want to lock this down. Yeah, all three of the services offer some way of either making the API endpoint private only to your VPC, or for the public endpoint, providing a whitelist of IP addresses which are allowed to connect. And read-only root file systems on the nodes are really useful because if somebody somehow gets access to the node, whether it's through a compromised pod or some other way, this prevents them from either installing their own crypto miner or maybe overwriting a binary that root may run with something that does something else. So Having a static file system is a much better protection. However, right now GK is the only provider that supports this, and it's only for the container optimized OS. Service limits are kind of a mixed bag, and some of these are really confusing. I spent a lot of time digging through these. Max clusters is pretty straightforward. Amazon, you can do up to 100 in a region. A lot of these you can request increases. That one I believe you can request an increase. AKS is 100 clusters period for each. What do they call their organization? I think subscription. Yeah. Azure it's a subscription. AWS it's an account, and Google it's a project. Okay. GK lets you have 50 per zone and a total of 50 regional clusters. There are a lot of zones, so you could actually have a lot of zonal clusters. Number of nodes per cluster. EKS, in a managed node group, you can have 1,000. I don't think there's a hard limit on self-managed because it's just a plain auto-scaling group. I'm not sure how many could successfully register with the master, though. AKS, it's 100 to 1,000. It depends on the VM type and some other variables around networking. GK, it's 5,000, except if you're using their ingress controller. And Kubernetes officially supports 5,000, up to 5,000 nodes in a cluster. Nodes per node pool, it's kind of all over the place. GK doesn't tell you how many node pools they support for a cluster, but the EKS and AKS, it's 10. Max pods per node. As I mentioned for EKS, it depends on your instance type. And it's also actually lower, much lower for Windows, if you're using Windows nodes, because they can only support one elastic network interface for whatever reason, although there can be multiple addresses on it. AKS, I have no idea that this range of numbers, I can't tell you which one, there's no clear logic or precedence. It will fall somewhere between 30 and 250. And GK is 110. Kubernetes right now still recommends 100 pods per node. No more than. So I do have the takeaways here, and these are my official slides. There's some kind of a few other differentiators that I will go into that are not on the slides. So obviously there are a lot of differences between these providers. GK is obviously both from what we've seen, and if you dig into the features that are available and just the general impression of their security offerings, their default security stance, by far the most mature, which you'd expect and hope. The thing about version promotion is a little weird, but otherwise they also offer a lot of neat things. You can, if you have very sensitive workloads, you can put those you can sandbox them in gvisor to isolate your other workloads. They have, let's see, there are a bunch of nice add-ons, and I'm blanking on a lot of them. Oh, they will install Istio, the Istio service mesh for you, and do the upgrades. They won't configure it for you, and that is by far the most work, but they will install it and do upgrades for you. You can install Knative. It will do the same. It will manage upgrades, but they call it Cloud Run, but you'll still have to manage it, the configuration. Obviously, AKS and EKS require more hands-on. It's not as automated, or you can automate it yourself, but it's not automated by the cloud provider. And this is all based on a blog post I wrote about a month ago, which you can read at www.stackrocks.com. There's a lot more information, but I'm going to go a little off the record here and talk about a few more things which are not really blogged or mentioned in the slides. Overall, I don't have any hands-on with Azure for protection. There are some network things that I wish they did better. The one thing my favorite thing about Azure, about AKS, they install the Kubernetes dashboard in every single cluster, and you can't delete it. And this becomes a security issue because the Kubernetes dashboard is not very multi-tenant friendly. So, to say the least. It is not open to the internet. It is a private service. However, that means any service, any workload within the cluster can also connect and have the same permissions. And there is no authentication on it. So there's no password protection. There's no token protection. So it's actually a serious issue. The only defense you have is to remove any RBAC permissions. And I just lost a little thing too. So that's probably the worst thing about Azure. Overall, most of these issues are manageable. You can, to some extent, with network policies, control some of your traffic. It is still difficult if you're using the Azure CNI to segregate pod and node traffic. In most cases, otherwise the differences between using KubeNet and Azure CNI. Azure CNI offloads a little of the overhead for networking, a little of the compute overhead, but it's not, I haven't benchmarked it. It's probably not a huge difference. You're going to have to trade that off with the fact that it is harder to secure. EKS is, so let me preface this by saying that if you have access to any of my personal data, please don't put it in an EKS cluster. The management overhead aside, it is very difficult to secure. And if you watch the updates, Azure has gone all in on Kubernetes. They regularly, obviously they're farthest ahead in the versions that they are at least in preview supporting, and they're constantly adding features. And some of these features are, yes, integrations with other Azure services, but a lot of them are just nice new Kubernetes features as they come and get released. Interestingly, Azure and Amazon released their Kubernetes services in the same month, June 2018. Azure has made a lot of progress, and they were both extremely, obviously, something they wanted out the door quickly. Azure has made a lot of progress since then. Amazon, not very much. And even now, they're not really adding a lot of really operability or security-wise features to EKS. It's mostly, when you do see something come out, it's mostly integrations with other Amazon services rather than core Kubernetes offerings. It's a lot of work to really manage a secure EKS cluster. It's a lot of overhead for the user to do, both initially to set up and to operate over time. Hopefully Amazon will step up and try to add some maturity to this product, but I haven't seen any sign of that. I would definitely reconsider if you have, and I realize a lot of people don't have a choice on which cloud provider they can use, but if you do have a choice, I would strongly recommend going to another provider. You do also have, if you are stuck on Amazon, and especially if you do have some resources, both skills and a little extra money, I would consider self-installing and managing something directly on EC2, whether it's COPS or kubeadm or OpenShift or something else. There are a lot of options that you can install and manage yourself. It'll give you, there's a little extra cost because you're going to have to, both financially because you have to run the masters yourself on EC2 instances, and there's a little more management overhead, but you do get a lot more control in return. So if you really want to secure it, you're stuck on AWS, I would strongly recommend considering that option. And if you have a good relationship with an AWS support or technical account manager, complain. Complain. They have the market share as a cloud provider, so I think a lot of people just default to trying EKS. It's like, oh, we have to do Kubernetes, but it's unfortunate that it's by far the least mature of the three offerings. So any questions?
Any thoughts on VMware going all in on Kubernetes and their cloud offerings?
VMware, they don't have a cloud service yet, do they? Then I'm.
They team Amazon, but They're changing their entire control plane in VMware to be Kubernetes.
Okay, yeah, the question is, what about VMware now changing, is like the vSphere type, okay, the vSphere, moving vSphere more towards Kubernetes. They're a little slow. I haven't looked at it personally, but I think that's showing, you know, we've seen that kind of move in a lot of places. Like Azure, when they launched, they had their own container service. It's gone now because they said everyone's going in on Kubernetes. Amazon still has their own container service, and it's much older though. They have a larger customer base, but it gets active development. I watch their announcements, you know, their release announcements. ECS gets new features every week or two, where EKS doesn't.
Have you looked at DigitalOcean at all? I
haven't looked at DigitalOcean. I would for VMware though. It's kind of interesting because, say for example, I know a lot of on-prem is also building on vSphere. On traditional vSphere, like Google Anthos requires right now, it only runs on vSphere. So it's both convergence and divergence. It's VMware is moving in the same direction, but so it's an interesting time if you're interested in how these versions kind of evolve, and it's almost the way, you know, viruses kind of evolve to some degree, so and spread, and then people get resistance, and yeah.
Sure. I mean, I actually have a question.
Okay.
So one of the things that's bothered me about all of these public cloud options is they all still require me to care about nodes. And if I'm going to use a public cloud dedicated Kubernetes service, the one thing I don't want to have to care about is nodes. Is anyone moving towards, you know, so-called nodeless Kubernetes in any kind of meaningful way?
Thank you for asking. So I used to have so right now, all right, AWS is one of their big announcements, one of their two big announcements for EKS at reInvent in December. Oh, hey, now you can use EKS on Fargate, so you can deploy EKS pods onto nodeless, which run on Fargate. Well, that's great, except for a lot of things. One thing is that you still need at least one node in your EKS cluster. Don't ask me why.
The second thing is there's a lot of restrictions on what kind of workloads they'll accept.
Exactly. Yes, exactly. The biggest restriction, and this is universal. So Azure also will let you do nodeless, and they use their container instances. And even though they're different implementations. Azure's is based on the open source virtual kubelet. Amazon's is some secret sauce, but they converge in what they allow you to do, interestingly. Daemon sets are not supported, so anything that you would normally want to run, usually monitoring or security or log metric collection or whatever, anything you would normally want to run on every node is not going to run. In most cases, you can convert this to a sidecar. It's not always useful. So it's useful if you, say, want log collection or metrics collection. But let's say you're running Calico because network policy, because, you know, security. Calico, yeah, you could put it in a sidecar. However, the other common restriction is that you cannot run privileged workloads on the pods, on the nodeless pods. And there are obvious reasons why, because this is not only, you know, Kubernetes is multi-tenant, but it's still all your resources. Fargate, Azure Container Instances, those are multi-customer, multi-tenant. So you don't know Joe Schmo, and you don't want Joe Schmo to have root on your machine, and he doesn't want you to have, So you can't, Calico has to change IP tables rules. That requires a privileged workload. They just silently fail. Even if the rest of your cluster has network policies, they just don't exist. They're ignored. They just, the nodes are, the pods on nodeless workloads just don't have network policies. Also means service meshes like Istio won't work because they also need to make modifications to the IP tables rules. So there are, even Amazon in their documentation for Fargate, EKS on Fargate, strongly recommends not putting sensitive workloads on these. And you also, if you really care about security and you're not just monitoring within the cluster, but you're monitoring the process calls, the actual network flows from the node kernel, you don't have that visibility. So these are, for some workloads, that's fine. For for a lot of workloads, that's going to be a deal breaker. And I don't know that that's something that's going to change anytime soon just because of the technology, that's the way Kubernetes and nodeless does and doesn't work. GKE doesn't have a nodeless option. There are some, you can kind of fake it using something like Cloud Run, but it's not really the same thing. Yes, both AKS and EKS do support nodeless, yeah, where the workload is actually on their container service.
Okay, I have one more question. I'm asking this because I'm part of SIG release in Kubernetes, which is, do you think the various clouds are stuck on 114 because they're just lagging a little, or because that was sort of the first production version they had, and they're going to be there forever?
I don't know. I don't think Azure will. Azure seems to, like I said, they seem to be going on all in, and they have 116 and 117 in preview. Okay. You know this. 116 has a big. They're removing a lot of older versions of APIs, the deprecated versions, like the beta versions. So this is going to be both internally for their services and for a lot of customers potentially an issue. And Azure does almost weekly notices about their current state of Azure releases, and they've just been, every time they're saying, oh yes, with 116, that's a big deal. So I think all will be slower when they actually move to 116, because it can be breaking for a lot of workloads. I honestly don't know. I mean, in the case of, I've heard rumors why GKE has become so slow on promoting. I don't know if they're true or not. I've heard rumors about why EKS is not making any progress. They're probably true, but I can't really repeat them. I have no idea. But even the documentation right now says it should be a 3-month cadence. They all say that, and they don't always follow through.
Thank you.
Thank you.